somewhere. Okay. I hope you see the slides. Everything fine? Okay, so let's get started here. Let me get my pointer straight. So we have seen an overview of the various methods, well, the physics and methods to calculate the excitation spectrum of a solid, the band structure. And we started dealing with the single electron dynamics, as I said, having struggled quite a bit to see how to solve the awfully complicated Schrödinger equation for the electrons and the ions in a crystal. One in principle would find the idea of moving electrons in the presence of an external field or external potential as a daunting problem. But actually there are theorems which simplify this task under some approximations. So I'll deal with this stuff that I call single electron dynamics, basically the acceleration theorems, how an electron moves, or the lattice, the crystal momentum K moves in the presence of a field. I'll give some applications, several examples. I think I have 5 examples of the possible problems that can be treated by looking at the single electron dynamics. I hope that I will be done by half of this marathon lecture. The second half will be a little bit of fun. I decided, after all, to include a little bit of information about special relativity. I'm not sure how many people have seen it before. I'll give just a rough overview. It will not be part of the exams or anything, but to give an idea about why we need to go beyond the Schrödinger equation. And I'll make some connection with a tight binding approximation which is used to deal with graphene. As you know, people say that graphene can be described to some approximation by the massless Dirac equation. It's a misnomer. I'll talk about it. There are 2 types of relativistic wave equation for particles with 0 mass, which were thought about to describe neutrinos when they came about, the Weil equation and the Majorana equation. And I'll give some idea about how they are related. Before doing that, though, I will, so probably I should swap 6 and 7 here. I want to review a little bit what we have done. I took some slides from a tutorial that I gave years ago, just to review what we have done so far and go into something a little bit different, which is, I think, of interest today, how to use, I should say, DFT or empirical pseudopotential methods to deal with structures which are not periodic in 3 dimensions. So nanostructures like nanowires, thin films, particularly today, there's a lot of interest about 2-dimensional materials. So how do you use these methods, which are plane wave methods? So in principle, they require periodicity in 3 directions. How do you tweak these methods by adding a fictitious periodicity in some other directions, so that you can use these plane wave methods to describe these nanostructures. And so it will be a review, but there will be a few interesting considerations about materials which are of interest today. So let's get back to what we are supposed to do now. We saw last time that we can describe the envelope equation, envelope wave function, in a way which can lead us to a single electron wave function, which is much simpler to solve than what we would expect in practice. I should say that during the week we had interesting conversations with particularly Professor Baccarani and Professor Gnudi about this issue, so I'll say a few words about it. Then we'll go into the acceleration theorems, and then we'll describe these examples that I give here. In particular, the last one is extremely important to deal with nanostructures and transported nanostructures. So last time we saw that if we want to solve an equation, the Schrödinger equation of our crystal, which I write here, if you set this external potential equal to 0, this is the equation that we've been dealing with. I remind you of all the approximations that we used. We separated the ions from the electrons by using the adiabatic or Born-Oppenheimer approximation. We went into lots of discussion, employing Slater determinants, how to go eventually into a single electron equivalent Schrödinger equation. I remind you that this parameter E is not really the energy of a single particle, or at least if you add this E for all of the particles that you have in a system, you do not get the total energy of the system because it's a system of interacting particles. So it's already complicated. And now if we're dealing with transport, for example, we have a device, an FET, a field effect transistor, and we apply, of course, some bias to the drain, the gate, the source. And of course, we have a field which is in addition, acts on electrons, in addition to the potential that are due to the ions. So how do you solve this problem? In principle, it's daunting, as I said. However, under some approximations, we found out that we can describe the, and I told you last time, the envelope approximation, the envelope wave function, which is, we consider the wave function, the full block function, which is given by an exponential times the periodic component of the wave function, which I remind you, these are the remnants of the atomic orbitals that we have. So they're functions which oscillate very fast spatially, as much as the atomic orbitals show very strong variations, spatial variations around the ions. And then this is modulated by a plane wave. So the idea here is that this describes, if you ignore the periodic part of the block function, this describes a free electron. We're going to pay a price, for example, by introducing a different mass, the effective mass. But essentially it tells you what the electron looks like, what its wave function looks like, in a crystal in which there is no external potential, just the lattice potential. If you apply an external potential, what we can do essentially under some condition is replace this plane wave by a slowly varying modulation factor, which we call the envelope. In particular, if you're dealing with electrons at the bottom of the conduction band or holes at the top of the valence band, so we expand, or we assume that we are considering only states which are in a small neighborhood of the minimum of the conduction band or the maximum of the valence band, then we can assume that this periodic component is roughly constant, and then it's modulated by something that now depends on a smoothly varying potential. Now, Professor Baccarani actually convinced me, something that I didn't know, that this equation is actually valid when we consider the full block functions in a single band, though. So we write our known as a combination of linear superposition of block states in a single band. And then if we apply a small potential, we find that this block function, or the linear combination of block functions, satisfies this equation. It looks like Schrödinger equation, except that the kinetic energy now is replaced by this funny object. E of k is just the dispersion of the electrons in a band, in a single band, and we replace the crystal momentum, the crystal wave vector k, with the momentum operator, so to speak, minus I times the nabla, the gradient. In principle, this is true. I didn't know, so I'm grateful to Professor Baccarani for having taught me something. In practice, the fact that you have to expand or considers only lunar superposition of electron in a single band demands some clarification. When can I do that? And the idea is that the potential has to be slowly varying. In practice, indeed, if you want to solve this equation, considering that this object is a very nasty object, if you can expand E of k, as I say here, a power series of the k vector, this will be a very complicated operator, whose mathematical properties, I think, that are not very clear to me, whether it's even a bound operator. But in principle, you can write it this way. In practice, you take only the leading terms of this expansion. Most often we take only the first term, which is the parabolic, the k-squared term, This gives us the Laplacian, and this becomes Schrödinger equation. So in practice, we chop all the high-frequency components of this unknown wave function, and we end up considering only the envelope. So the two derivation, if you wish, become equivalent. So last time we saw the derivation following essentially what Lattinger and Kohn did in 1955. Their idea was to deal with this problem when the external potential is the potential of a dopant, a charge impurity. The problem that they wanted to solve at the time, which we'll deal with, was to find what is the ionization energy, say, of boron or phosphorus, substitution in silicon, so a dopant, p-type or n-type doping, the boron p-type and phosphorus n-type. And this is supposed to be a slowly varying potential, and we will see. So consistently, we can find that this is a good approximation. And so essentially what they wanted to solve was a hydrogen-like equation for the electrons with some corrections, mainly the mass becomes different. So they went through the derivation on when can I do that? What is the advantage that I get from considering a potential which varies slowly? Very slowly means that the variation of this potential over a single cell is much smaller than the energy you're interested in. This instead varies extremely fast, and the energies that you're dealing with are of the order of several Rydbergs. A Rydberg is the ionization energy of the hydrogen atom. So we went through this derivation, which is as they usually say, tedious but straightforward. You can rederive the Schrödinger equation in this form by expanding the unknown into block functions. You take a linear combination of these block functions, you do some manipulations, and eventually you can find that these coefficients of your expansion have to satisfy a system of a linear system of equations. You realize that this is a system in which this is the diagonal part of the matrix. This is, if you want, your eigenvalue, and these are the off-diagonal components, and this is the big problem. This is fully equivalent to the general equation, the general Schrödinger equation we started from, except that this is now, in principle, is complicated because this matrix element of the external potential sandwiched between wave functions in different bands for different k points, they can all be non-zero. In general, they will be non-zero, and so our system of equations is extremely complicated. So the way to deal with the problem is to find under which conditions this term becomes essentially diagonal, so that transition between bands are ignored, which implies that this potential has to vary slowly, which means the field associated with this potential is weak, and then there is no interband tunneling of the electrons. And if we do that, if we make some approximations, let me skip what we did last time. If we assume that the external potential varies slowly, that we're considering only a wave packet which is a superposition of states in a very small neighborhood of some particular point I'm interested in. If I'm computing, for example, the electron mobility in silicon, I will consider only k vectors which are in a small neighborhood, such that their energy is within a few kT around the minimum of the conduction band. If we do that, then indeed we find that indeed this matrix element of the external potential are diagonal. Again, there is a swiggle here because of these approximations that we have to make. So the electron under a weak field remains in one band, and having done all this procedure, satisfies this equation. If we take only the leading term in the expansion of E of k, expanding around the minimum of the conduction band, we find that this is just a parabolic dispersion given by an effective mass. I'll describe it in the next slide, how to derive it formally. And so essentially what we find is that our very complicated problem of dealing with an electron in a crystal, so feeling the potential of all of the ions, and in the presence of an external potential that doesn't vary too fast over a unit cell, it's reduced to solving a Schrödinger equation, exactly like an electron in free space, but in the presence of this external potential. The only hint that we're dealing with the crystal is given by the fact that the mass is not the mass of a free electron, but is an effective mass, which is essentially what we get by expanding E of k around the minimum. So this brings us to the concept of the effective mass. I take E of k, as I said, we expand it into a power series around some particular point k0, the minimum of the conduction band, the top of the valence band, in which case this would be 0. And what we do, we expand in Taylor series. The first term, since I'm, by definition, I decided to expand around the minimum or maximum, where the gradient is 0. The first term disappears, and I'm left with the second term, and I'm ignoring the higher order terms. Symmetry usually tells us that, for example, for the valence band, we're going to have only even powers of the k vector displaced from the minimum. This is a funny notation in which I mean the second derivatives of the energy with respect to kx, ky, and z, dotted with the displacement of the k vector from the minimum. So having done this expansion, the idea would be to replace, as we saw here, to replace the k vector with the momentum, except for the h bar, and we find that our operator becomes simply a constant, which is the energy at the extreme point, the bottom of the conduction band or the top of the valence band. And then there is a term which is essentially a Laplacian. The only complication is that in principle, this is not a diagonal matrix. Okay, in some simpler cases, like for silicon in the bottom of the conduction band, this second derivatives, the matrix that expresses second derivatives, okay, becomes diagonal because of the symmetry of the lattice, which is cubic for silicon, and for silicon, for germanium around the symmetry point L, for example, one can find that the effective mass tensor, which is defined such that our second order matrix can be written in this form, so this represents the definition of the effective mass tensor, is a diagonal. Two terms are the same, what we call the transverse masses, and one term is different. So, for example, for gallium arsenide, these numbers will all be the same. The minimum of the conduction band is at the symmetry point gamma, which is at k equals 0 at the center of the Brillouin zone. As long as I don't move too far away from that point, the symmetry of the crystal is essentially spherical. As I begin to move away, I begin to see the cubic symmetry, but if I stick very close to the gamma point, it's symmetric. So essentially all I have is a spherical parabolic dispersion, like electron in free space. So equi-energy surfaces will be spheres, and I can talk about a single effective mass. And then my Schrödinger equation over here becomes exactly as I wrote it here. In general, I have more complications. This term will not be diagonal, and so I have to deal with different effective masses as written here. For silicon, the equi-energy surface is around the symmetry point, along the symmetry line delta, very close to the symmetry point x, which is the 1, 0, 0 point in units of 2 pi divided by the lattice constant, is an American football or a rugby football. So a ellipsoid of revolution. And I can write a Schrödinger equation which clearly is much simpler than the extremely complicated Schrödinger equation that I wrote here at the beginning, which in principle is a nightmare. We saw already how complicated it is to solve it when this is 0, and now we're adding a complication. Yet, with the restriction that I'm dealing with a single band, that I'm not moving too far away from a particular point, the minimum of the conduction band, for example, I can write this equation in much simpler terms, an equation that I can solve. So I'll show you some examples of how this equation is used, for example, in silicon inversion layers. I'll give you an explicit example, actually with numerical results. As far as I know, actually, this was the first time that it was used beyond the work that Lattinger and Kohn did in 1955, when people finally were able to fabricate field effect transistors. The idea went back to, I believe, the 1920s. In practice, the first FET was made only in the mid-1960s, I think 1964. And the first time that people used this equation was to study what happens in an inversion layer of a field effect transistor, how electrons are quantized. And I will show you the example for silicon as using this equation to solve that particular problem. This equation goes under many names. If we use it this way, we can talk about the envelope, equivalent Hamiltonian, as Professor Baccarani calls it. If we consider this is the full block function, in practice, if we expand it, only keeping the leading terms of the power series of this term, we consider only the the spatial frequency components of the wave function. So we consider only the envelope. So sometimes it's called the envelope wave function approximation. I like to call it Kohn-Lotinger equation. Sometimes it's called effective mass equation, simply because in practice you have to introduce the effective mass in order to solve it. But its validity is more general than just effective mass. And I should also mention the fact that it can be extended to many bands. You pay a price, you don't get the simple equation, but you get a system of equations, depending on how many bands you are coupling. So that would be the rank of the linear system that you have to solve. But it can be generalized in many ways. Although, of course, as soon as you generalize it, the complications, the mathematical complications increase, and then it becomes more laborious to solve it, if you can solve it at all. Okay. Let's go back to single electron dynamics. The point that I want to make here are there are two basic theorems. The two theorems are stated here. Let's call it acceleration theorem number 1 and acceleration theorem number 2. This is actually a velocity theorem. If we consider an electron in our same conditions that we see here, okay? So we have the electron in a crystal, and we apply a small electric field. We mean spatially varying. Small electric field means that, as I said, this potential doesn't vary too much over a unit cell, where too much means the variations are small compared to the energies of interest that we're dealing with. So the first idea is that the velocity of the electron is given by essentially what we can call the group velocity of a packet. I hope you remember from the theory of electromagnetic waves that there are two different velocities that you can describe for a wave packet, which is a linear superposition of plane waves. You have the phase velocity, which is simply the frequency divided by the k vector, omega divided by q, or by k, whatever you call it. Clearly for electromagnetic waves in which omega, the frequency is given by the speed of light times k, omega divided by k is just c. So the phase velocity is just the speed of light. Or you can have the group velocity, which instead represents, if you have a packet, how fast the packet moves spatially. For electromagnetic waves, it doesn't spread. And the phase velocity for electromagnetic waves with a linear dispersion, omega equals ck, is equal to the phase velocity. But in principle, this can be different. You realize that this expression, the group velocity of the electrons, will be different from the phase velocity because you have a parabolic dispersion, k squared. So the first theorem that I will prove in some heuristic approach is that actually the velocity of an electron is given by the slope of the band structure. Okay. The second theorem, which is relatively more surprising, if you think about it, it's very surprising, is the fact that if I look at the time evolution of the crystal momentum, so this is the parameter that labels a block function, for example, or it says where in the Brillouin zone my electron sits. If I apply an external potential, so an external field, which is given by the gradient of the potential, the k vector moves in space essentially according to F equal ma. This is just the force. If I multiply h bar, I move it away and I bring it to this side, this will be dp dt, as I wrote here. So this is the time derivative of the crystal momentum. And this is equal to minus E times the electric field, which is just the force. So this is F equal ma, which is sort of surprising. One can use a very heuristic approach that I will describe, although it's heuristic, but there's more to it. It's not fully empirical. And the way to prove it is relatively simple. So the two theorems, just to repeat, is if I have a fixed electric field applied to the crystal, then the acceleration, which is the variation in time of the k vector, is given by this simple expression. Again, bring h bar to this side. This means dp dt, the derivative of the crystal momentum with respect to time, is equal to the force that I have. And this can be extended to a slowly varying electric field. Exactly in the same spirit that we saw for the Cohn-Lattinger equation, envelope equation, whatever you want to call it, exactly in the same spirit. As long as the electron doesn't jump to another band by tunneling in k-space and going to the next band, if the field is very strong, this is a process that indeed may happen, then we get essentially F equal ma. It's kind of surprising because, well, I will show you, I think in the next slide, how surprising it is, because essentially it tells you that if I have an ideal crystal, I ignore all collisions. So the k vector revolves only in time, only under the effect of the field. You get a surprising conclusion that you get no current, because E of k, I'm sorry about the fact that the electric field is often called E, we call E also the energy, but the dispersion of the electron is periodic in space. And so the electron will just move up back and forth in a crystal oscillating. And this indeed is the concept beyond the Bloch oscillations. So ironically, you need scattering to get current in a crystal. The second acceleration theorem is that the expectation value of the velocity, to put it more formally, on a given Bloch state is just given by the gradient of respect to k, so in k space, of the dispersion of the electron in that band. I say here, in absence of magnetic fields, actually you can generalize it also. In the presence of magnetic fields, and you get Lorentz, the same expression that you get from the Lorentz force. So how to prove it? The proofs are a little tricky. One proof that I like quite a bit is proving theorem 1, assuming that theorem 2 is true. And I will give you a brief sketch. Well, if we want, that's the proof of theorem 2, sort of heuristic. Let me write the effective equivalent Hamiltonian of the crystal as we saw it in equivalent Hamiltonian formulation of the Schrödinger equation. So we have a kinetic energy term, which is the dispersion of the electron in a single band. This is K, it is just P divided by H bar. So this is kinetic energy. So all the effects due to the ionic potentials, the complicated terms, are lumped into this term, which of course is hard to solve, as we saw when discussing how to calculate the band structure of a crystal. And then we have a potential energy term. Let me consider this as a Hamiltonian. Then Hamilton equation tells us that the derivative time of the position, the canonical position coordinate, is equal to the gradient with respect to the canonically conjugated momentum of the energy. So this is a heuristic approach, but actually can be proven rigorously by using what's called the Hellman-Feynman theorem, which is a theorem which says that the Hamiltonian depends slowly on a parameter. Then you can write the expectation value of anything by treating that parameter, taking derivatives with respect to that parameter. I'm not going to go into it, but it's more rigorous than it looks like from the simple approximation. Again, this is true if I can stay in a single band, so if the potential is varying slowly. So assuming that, so having proven, so to speak, that theorem number 2 is true, then what we can do is consider to prove theorem number 1, which is F equal ma in a crystal, is to consider which is the power. So the variation in time of the energy of an electron, let me call it W, to not to confuse energy with electric field. So the time derivative of the energy that an electron has will be given by, of course, the acceleration that it feels, so that the electron feels. So it will be the force times the velocity. The force is just the electric field. if this is an electron, there is a minus sign, if this is the magnitude of the electron charge. And we know from theorem number 2 that the velocity is just the group velocity. So it will be 1 over h bar times the gradient, which is what I plugged into here. On the other hand, the power that we have can also be written as the time derivative of the k vector with respect to the velocity. Okay, so by making it, just taking the derivatives, the chain rule for the derivatives. So I take the time derivative with respect to time of w, but w is just e of k. So I take first the derivative with respect to k and then the derivative of k with respect to time. Chain rules of the time of the derivatives. So by looking at comparing these two, we see that this term has to be equal to this term, which is exactly the acceleration theorem. One can use time-dependent perturbation theory as well. The second book by Kip Dow shows the derivation. The book by Brian Ridley that I gave you, and I think it's in the syllabus of the class, also gives a derivation. And one can generalize it also to account for the Lorentz force in the presence of a magnetic field. So this is the first, the second theorem, so the first theorem, and I said it's kind of surprising. So here, I apologize for the low quality of the sketch here, but suppose that this is the band structure of the material, this is the first Brillouin zone, this is the next Brillouin zone, and this will continue periodically over all the Brillouin zones. If I look now at my acceleration theorem written here, if I apply an external field pointing towards the left, the electron will be, excuse me, the electron will be accelerated to the right, so its k point keeps moving, its k vector keeps moving following the band structure, okay, from one Brillouin zone to the next, because of the periodicity of the dispersion. So because of the acceleration theorem, you see that here the electron has zero velocity. The velocity in this simple picture is just the slope. Then it begins to accelerate. At this point that I marked here, there is an inflection point. So the velocity actually changes sign. The electron begins to move backwards. Then it stops. Spatially, oops, my apology here. Okay. Spatially, the electron will go backwards. Then it will continue to go backwards. Then eventually will begin to move forward again. At this point, because of the symmetry of this dispersion, the electron will have gone back exactly to the same point where it started from. So the electron has undergone an oscillation. Started spatially, it moves, starts from one point, it accelerates, goes back, and then it comes back to the same point. So it has undergone an oscillation. That's why I said that if in a crystal we ignore scattering processes, there's no current. There would be some spatially varying current of electrons which go back and forth, but there will be no net flux of charge throughout the entire device. And these are called block oscillations. We can calculate relatively simply what is the frequency of these oscillations. For the electrons to go through an entire oscillation, the k vector has to go through an entire period of the Brillouin zone, 2 pi by a. This is, forgetting the minus sign now, I'm looking just at magnitudes. The field, the force multiplied by the time gives us the total displacement of the electron in k space, and this has to be equal to the size of the Brillouin zone. So this is the period of the oscillation. The electron will keep going back and forth in k space and in real space with this period. Therefore, we can extract immediately the frequency of this oscillation. And also we can immediately find out by this simple theorem plus knowing what the velocity is, which is just the group velocity of the packet, we can find which is the length of the oscillation in real space that the electron has gone, which is the width of the band divided by the field and these factors. So these are oscillations, and actually people looked, if I remember correctly, in the mid-80s, going to any conference which dealt with of equilibrium phenomena in solids, hot electrons or whatever. There was a conference called the Hot Electron Conference, and now it's called Edison. I think that there were more than three sessions all dealing with block oscillations. The problem that you find is exactly the same reason why you do have current in a crystal. These oscillations occur only if the electron can travel without collisions through the entire oscillation, so through the entire period. Now you can estimate what is the period in a crystal, and you find that it is much longer than the typical scattering time that you have. Collisions with phonons, which are thermal vibrations of the ions, collisions with other electrons, collisions with the dopants if you have the doped semiconductors, whatever you're colliding with. So the problem is that these oscillations are disrupted, they're killed, damped if you wish, by collisional processes. And so given the width of the band that you have, you see that the length over which the electron has to travel increases linearly with the width of the conduction band, for example. In a crystal, this may be several electron volts. This distance will be much, much longer than the electron mean free path. And so one doesn't see them. The idea would be to go to artificial lattices called super lattices, in which, for example, you stack layers of indium gallium arsenide and aluminum gallium arsenide. You keep stacking them. There is an artificial crystal, much like in the Koenig-Penning model that we saw before, and you can have what are called mini bands, bands which with width is much smaller than the bandwidth that you have in a solid. This means that this distance would be much shorter, and then you have a chance of creating terahertz oscillations. Here I show what the picture looks like. It's also called Stark ladder quantization. In a field, I have electrons which in this band can move back and forth, of course. Normally, there are electrons in our band structure. If I apply an electric field, then this is the width of the conduction band, for example. Electron moves back and forth. This is spatially. And so this results in what's called the quantization of the electron motion. And I show here that indeed the frequency of these modes, of these oscillations, can be relatively small, and which means that scattering is going to kill these oscillations. It takes too long for an electron to go through an entire oscillation. This is the first result that one can see about the acceleration theorem, because it follows directly from the acceleration of the K vector, the crystal wave vector of the electron in a lattice. The second application is, well, strictly speaking, I'm not sure whether you've ever seen the solution of Schrödinger equation for an electron in the presence of a magnetic field. This is an issue which is quite important in two-dimensional systems, in a two-dimensional electron gas. Historically, the problem was first studied experimentally and theoretically in silicon inversion layers. One can see them in quantum wells of 3-5 compound semiconductors. If I have a sheet of electrons which are confined in 2 dimensions, such as in the silicon inversion layers, and I apply a magnetic field which is perpendicular to the sheet, to the 2-dimensional electron gas, then I can write the acceleration theorem using the equation that I wrote before over here. So forget the electric field for now. We simply have the Lorentz force acting on the electrons. So I can write the acceleration of the K vector in terms of the magnetic field using the Lorentz expression. If B is oriented along the Z direction and I have my 2-dimensional electrons in the XY plane, then these are just the expressions for the equations of motion that you get from the V cross B term of the Lorentz force. B is the magnitude of the magnetic field. Of course, you can solve them in the usual way by replacing taking the second derivative with respect to time of one equation and plugging it into the next. And I think you're familiar with this. You get 2 equations which are harmonic equations, which tell you that the K vector, or the velocity of the electron, which is proportional to the K vector, oscillates in time with a frequency which square is given by this expression. The electric charge times the field divided by the effective mass of the electron. Of course, I should have said before, I'm dealing with a parabolic dispersion, so I'm looking at the motion of the electron close to the bottom of the conduction band. For a free electron in free space, clearly this m star will become just the electron mass. And what you have, they are what's called as cyclotron orbits. The k vector, so the velocity moves harmonically, and so the electrons follows orbits, and the frequency at which they oscillate around these orbits is given by this expression. So it's linearly proportional to the magnetic field and inversely proportional to the mass. Quantum mechanically, so this actually we know that is correct also quantum mechanically in a lattice because of the acceleration theorem. If you want to go a little bit deeper and see how the electron motion is quantized into these objects, I hope you suspect that there's going to be some quantization here. It's a harmonic oscillator. Classically, any orbit will be allowed, any radius, any frequency, but quantum mechanically, we're going to have excited states very much like we have excited states in a harmonic oscillator in 2 dimensions. So the motion of the electron will be quantized. To do that, you have to add a magnetic field to Schrödinger equation. How do you do that? That's where we need a little bit of relativity, so to speak, to justify it rigorously. But the empirical rule, and I have to say, take my word for it for now, it's to follow what's called the minimal coupling. We'll discuss it a little bit, or at least it will be apparent when we'll discuss about a little bit of special relativity. What you do is you replace the momentum of the electron with the momentum plus the vector potential of the magnetic field that you have. The idea is that the momentum is the 3 components of the momentum are the 3 spatial-like component of a 4-dimensional vector, which is what you have to deal with in electromagnetism, because Maxwell equations are not invariant anti-Galilean transformation. We'll talk about it. This is the vector potential A. The 3 components of the vector potential A are the 3 space-like component of the potential, the 4-dimensional vector, whose time-like component is the potential phi. Sorry that I use phi also for the wave function here. So P and E are the 4 components of the energy momentum vector, which is relativistically invariant. A and phi are the 4 components of the relativistic potential, so to speak, of an electromagnetic field. So the idea is that you add the space-like components of the energy momentum vector to the space-like component of the potential, the 4-vector of the potential, electromagnetic potential. So this is what's called a minimal coupling. So all you do to account for the presence of an electromagnetic field in Schrödinger equation is replace P with P plus E sub A. Occasionally you have, depending on the units that you use, you can divide by speed of light over here. You have an E over C in Gaussian units. So if I have a magnetic field which is pointing in the z direction, it's trivial to see that the vector potential, such that the curl of A is equal to B along the z direction, is given by this expression. So now you plug it back into Schrödinger equation. I don't want to go into too many details. Again, don't worry too much about it. If you've seen it in quantum mechanics already, good. If not, you can do some manipulations of your Schrödinger equation, which now has this nasty form, okay, for a plane wave. And what you have is that you can recast it into a form which tells you that you have the motion of an electron in the presence of magnetic field along the z direction will be given by a uniform translation along the z direction, which is the kinetic energy along the direction parallel to the magnetic field. But in addition, the electron will undergo orbits, exactly what we saw here, okay, like a classical electron in a magnetic field, something that you see in plasma physics, for example. And the problem is that this must be quantized, of course, because it's a harmonic oscillator and we're dealing with quantum mechanics. So indeed, what we see, we can factor out the various terms in a different form, and we can write the Schrödinger equation in this form, in which you have the motion along the z direction, the harmonic oscillator p squared plus r squared, which is the harmonic oscillator in 2 dimensions in the xy plane, and this has to be equal to the energy of the system plus the translational energy that I've divided in this way. So the motion of the electron will have a portion of the spectrum which is continuum, which is given by the translation along the z-axis, and a portion of the spectrum which is discrete, which is the result of having to quantize this harmonic oscillator. You can quantize it many ways. So what usually one does is factor out or separate the variables of the unknown by writing the unknown wave function as a product of a wave function that depends only on the z-coordinates. The z-coordinates is parallel to the direction of the magnetic field, and a wave function which depends only on the in-plane coordinates. Having done that, you find that you can write the in-plane portion of the equation in terms of the Hermite polynomials. If you have not seen the harmonic oscillator in quantum mechanics, let me know. We will see it in a different way, in the Dirac's algebraic fashion. But the solution of harmonic oscillator in quantum mechanics gives a wave function which is given by some polynomials damped by an exponential term, a Gaussian term. And this instead is the free motion along the z-axis, this pz term, which gives us this continuum spectrum and plane waves along the z direction. So what we end up with is that the eigenvalues of my system of a two-dimensional electron in the presence of a magnetic field which is along the direction perpendicular to the plane is given by the continuum portion, motion along the z-axis, plus this revolution term, the harmonic oscillator, that is quantized. And again, the eigenvalues of the harmonic oscillator are given by the h bar omega c, where omega c is the frequency of my harmonic oscillator, which is the cyclotron frequency. That's why the c is here, which again is given by this term. And the ground state is 1/2 h bar omega c, and then you can have excited states which are equidistant in terms of energy. So the energy spacing between the levels is the same. So you can move up through excited states in integer steps of h bar omega of the harmonic oscillator. These levels, so you have an electron in a magnetic field, so moves along orbits, which again are quantized, and plus it can move, as illustrated here, along the z-axis. Okay, I should add, if you also have an electric field in the xy plane, these orbits can drift, accelerated by this electric field. Let's ignore it for now. Now the question is, these levels, which are called Landau levels, these are the energy levels that you have resulting from the quantization of the eigenstates of the electron in the presence of a magnetic field. Suppose that the electron don't move along the z direction; they are stuck in z equals 0 plane, the xy plane. Then what you have is that the spectrum of your excitations is given by these eigenlevels, which are called Landau levels, but they are degenerate. What is the degeneracy? Well, we have to count how many possible combinations of kx and ky in the xy plane you can have that correspond to the same orbit. So what we do, we call this degeneracy. This factor g is the number of states that we have in each Landau level. And this will be given by the number of k states that we have in a small shell of thickness delta kr for each orbit. And it's given by 1/2 pi squared. This is just the usual factor that you get by integrating states in 2 dimensions, or counting the k points in 2 dimensions. Then we have 2 pi k of r is the circumference of an orbit in orbiting k-space times its thickness. And so it's given by this expression. Okay, now this must mean that if I change the radius of the orbiting k-space in a given step, this for this given step must be equal to the jump that I have between two of the states of the harmonic oscillator. So you do a little bit of algebra and you find that this is the degeneracy of the Landau levels. So each Landau level has the same energy, but there are a number of possible combinations of kx and ky that give me the same k that quantizes that state, which is given by this factor. Again, as in the case of the block oscillation or Zener block oscillations, you can have an electron orbiting an orbit in this Landau level only if scattering does not disrupt its orbital motion. So you have the same situation. Indeed, Landau levels were observed for the first time and are usually observed, except in some particular situation, at cryogenic temperatures. You want to suppress all possible scattering processes so that this condition is verified, okay, which imposes a condition on the magnetic field. So typically, in order to see Landau levels, you must have a strong magnetic field and low temperature. And typically you need a magnetic field of a few Teslas in order to see them. This was the first, if I'm not sure if I'm fully correct historically, but it was the first time that people saw that indeed you have a two-dimensional electron gas. Professor Baccarani may remember that this happened at IBM in Yorktown in the mid-60s. It was the very first observation of a quantization dictated by this equivalent Hamiltonian equation. So historically, it was very important. The field of two-dimensional electron gas now has blossomed into its own huge literature, and it's an extremely active field of interest. And now we're dealing also with one-dimensional electron gases. There, the physics is even more complicated. Is there a question? Is there a question? No? Can I go on? Yes? I see some noise, I hear some noises. Okay. The third example that I want to give, you may wonder why I talk about plasma oscillations. So plasma physics is a big field and I'm not an expert in that, but plasma oscillations in a solid are quite important. And actually it will be the main example after Schrödinger field. The main example, because it's the simplest, of how to quantize elementary excitation in solids, which is, if you want, the core of this class. I think we'll start hopefully next week. It's a relatively simple example. In addition, I'm particularly attached to this problem because it involves, it's related to dielectric screening and lots of interesting phenomena that are extremely important in the nanostructure that we're studying today. So let me give first an example of what I mean by plasma oscillation. I stole this picture from the web somewhere, but jotted down the basic equation that we want to deal with. Suppose that I have a slab of electrons, which are the little minus signs that you see here, and there is a background of positive charge to keep things neutral, to prevent them from exploding. And let's assume that the system is perfectly neutral, and now by applying an electric field or by just with tweezers pulling the electrons in one direction, I displace by an amount delta x the electrons from the ions. So on one side of my slab, I have a charge density negative. On the other side, I have positive charge density. And the charge density sigma, the two-dimensional charge density, will be given by the electron charge Okay, in this case it's negative because I'm looking at electrons. There is a little minus sign here, times the density of electrons that I have, and 0, a uniform density, times the displacement. So this clearly has dimensions of Coulomb per unit area, per square centimeters. So if I look at a single electron sitting here in this lab, what is the force that is acting on this electron? Well, so let's write F equal ma. Ma will be just given by the electron mass times the second derivative with respect to time of the displacement that I have as the negative and positive charges move back and forth. Let's assume that the positive charge is fixed and the negative charges are moving. So the mass times acceleration term has to be equal to the field. So an electron sitting here feels a restoring field due to the charges that you have on the two sides, which gives rise to an electric field. The electric field, by simple electrostatics, is just given by the charge divided by the dielectric constant of the medium multiplied by the charge density. The charge density, we already saw what it is. It will be E squared n divided by times dx, and then there is a divide by epsilon. So the square comes because I have a E over here for the charge, an E for the field, for the force, and then I have an epsilon in the denominator, which means that the second derivative of delta x with respect to time is equal to omega squared delta x. This is again the equation of a harmonic oscillator, which frequency given by this term. So the frequency, we call it the plasma frequency, is given by something which is proportional to the density of the electrons and ions that I have over here, inversely proportional to the mass and the dielectric constant of the medium. What happens physically? If I move the electrons this way, they feel an electric field pulling them back. So they will begin to move back, they will overshoot. So now I will find a situation which is the mirror image of what I have here. I will have negative charge over here and positive charge over here, and the electrons will stop, and then it will begin to accelerate backwards. So exactly like I'm in a pendulum, they will keep moving back and forth with a frequency which is given by this quantity, which is called the plasma frequency. We can derive it in a solid using the acceleration theorem, as we saw before. In addition, we need, of course, to do a little bit of electrostatics. So we have the crystal momentum of the electron, the crystal wave vector of the electron is changing in time because of the electric field that I have. The electric field can be obtained by Gauss' law. If I have a uniform electron density, but then at some particular point I change it a little bit by delta n. Suppose that the delta n is the change in the electron density. The charge density that I will have, sorry for my clock. Now it's 11 because we have an extra hour. Okay, we're done. Sorry about that. So this will be a positive charge, which is the charge of the positive gallium, the background of positive charge that I have if I remove electrons on one particular position. Of course, if I take them away from one spot, I will have to pile them up in another spot. That's the origin of the oscillations. So this is the relationship between the field and the density. On the other hand, I have a continuity equation that tells me that the change in the density at a particular point as a function of time has to be equal to the opposite of the divergence of the flux. The flux of what comes out is given by the velocity that I have times n. The velocity, I know what it is. It is just h bar k divided by m star, if I'm assuming a parabolic dispersion. So plugging everything together, if I take the second derivative with respect to time of this, I get the derivative of second derivative of this object, which is the time derivative of the divergence of the flux. Let me assume now that which I can write it this way by swapping the time derivative with the nabla symbol. Let me assume that the density to first order is fixed. This will be just the gradient of the derivative of the velocity with respect to time. Then let me bring the n out because it's a higher order term. So I have that the second derivative of the charge density with respect to time is equal to this expression. So it's proportional to the derivative with respect to time of E. Now I use finally my acceleration theorem that I hadn't used yet, and I find that the second derivative of the charge density with respect to time is equal to the minus the square of the plasma frequency in my medium. It's exactly the same expression that I had before. I wrote epsilon s instead of epsilon over here to say that this is the epsilon of the solid semiconductor, whatever you want to call it, times delta n. So again, it's a harmonic oscillator, and we recover the same result. If I have a homogeneous electron gas in the presence of a gallium, if I take away electrons from one particular spot and I move them away, then the electrons will be attracted back to the position where I took them off because of the positive charge that I have here. In so doing, they will generate a wave. They will go and try and move towards the positive charge. They will overshoot it and begin to oscillate back and forth. In general, though, this wave can propagate. If you think of a plane wave, I take a line of positive charge because I move the electrons away, and this will keep moving at some velocity, which is given by the group velocity of the plasma. Actually, it's almost zero, it's very small, but you have a plane wave. So the solution of this equation is an oscillatory term. And, excuse me, and we will see that indeed this will be the first system that will second quantize to see how to deal with this in quantum mechanics. Maybe you can see already why we will talk about second quantization in some sense. Here I'm using an acceleration theorem to go from here to here, which is, so I replace the kdt with the electric field, having used the acceleration theorem, which is coming from, if you want, quantum mechanics in a solid. And I get an equation which I will later view as a classical equation that has to be quantized. And historically, that's why people talked about second quantization. It's a misnomer. That's not the logical way, the correct way to deal with the problem logically. So we will discuss about it. Okay. So it was 11. Let me work on half an hour before taking a rest. I said at the beginning that Latinger and Kohn dealt with the equivalent Hamiltonian equation that we saw at the beginning by looking at the excitation spectrum of shallow impurities. Well, shallow has yet to be determined. The idea is I have, as I said, say, boron or phosphorus. Let's take phosphorus in silicon. Phosphorus is an element of the fifth column of the periodic table. So it has 5 electrons in the outer shell. If I take a silicon out with tweezers from my crystal and I replace it with phosphorus, I have essentially the same situation. 4 of the electrons of the phosphorus will go into the 4 tetrahedrally coordinated sp3 hybrid orbitals, but then I have an extra electron. So is this electron going to be free to move around? Of course, I have, if I take away this electron for phosphorus, I have a positive charge because I have replaced silicon, which is a +4, with phosphorus, which is a +5 in the core. So the question is this electron going to be free to move at room temperature, or instead, is it going to be tightly bound to the phosphorus? In the first case, I do have doping, which is what I'm hoping for. In the second case, no. I have an impurity with a deep trap, if you want, and the electron is trapped there for good. So the question is whether the energy of the state is sufficiently close to is in the gap, but sufficiently close to the bottom of the conduction band. Sufficiently close means of the order of kT or less, so that at room temperature, that state can be ionized and the electron is free to move. So I need to have an estimate, at least an estimate, of what is the energy of a quote-unquote hydrogen atom, which is the plus charge that I have in a solid, so represented by a potential, which is the hydrogen-like potential, except that I'm hoping I can replace the dielectric constant of vacuum that I have to consider when I'm dealing with a hydrogen atom in vacuum with the dielectric constant of the material, of the semiconductor, say silicon. There is a little bit of a problem here. The dielectric constant is a macroscopic object. So I can define the polarization. We will discuss it in detail later, but in the next few weeks. But I cannot describe or consider a microscopic dielectric constant. Actually, there are some arguments among many physicists that a microscopic dielectric constant is a nonsense intrinsically. One can define it as long as we agree on the definition, it's okay. But I can replace this dielectric constant of vacuum with a dielectric constant of silicon only if the orbit, the electron around the impurity spans several unit cells, so that I can assume an average polarization of the electrons and the ions average over many cells. So eventually, at the end of the calculation, if I start by assuming that I can do that, if the radius of the orbit of the first excited state that I find, or the ground state, I should say, that I find, is of the order of a single primitive cell or cubic cell of silicon, then I would have an intrinsically, internally inconsistent approach, because I'm assuming a macroscopic object and I'm applying to a microscopic situation. So we'll have to do a check at the end. So the idea that Conrad Luttinger had was, let me go back to the equation. Let me go back several slides that we started off. Where is it? This equation. Let me assume that I can use an effective mass, which is the effective mass at the bottom of the conduction band. For simplicity, we can consider some isotropic material like gallium arsenide. And let's solve the equation for the hydrogen atom, where the external potential now is just the potential of a single ionized charge, ionized impurity, a single charge, with the microscopic dielectric constant of the medium. So the algebra, I should say the calculus, will be exactly the same that we follow for the hydrogen atom, except that now we have two quantities which are different, the effective mass and the dielectric constant. Now we know that the radius of the ground state of the hydrogen atom is the Bohr radius, which is about half an angstrom. And it's given by this expression. The binding energy of the hydrogen atom is given by this expression, the Rydberg, which is about 13 electron volts. Now, for the radius, and that's what we need to do in order to verify that we're doing something consistent, what is the change? Well, this epsilon zero, the vacuum permittivity, now is replaced by the dielectric function, the electric constant of the semiconductor. It's typically the order of 10. It's 11.7 for silicon, 16 for germanium. It's the order of 12, 13 for most of the 3-5 compound semiconductor. So let's take it as the order of 10. Order of 10, this brings us to 0.5 nanometers. That's about the size of a unit cell. But we have an effective mass. If I consider gallium arsenide, for example, this mass is about 0.06. So this is more than an order of magnitude bigger yet. So we go to 6, 7 nanometers. For silicon, okay, we can consider an average mass of 0.3, something like that. So it's not quite an order of magnitude, but almost. So we get to something which is the order of between 1.5, 15 angstroms, which is about 3 cells cube. We're taking an average over 3 cube cells, 30-ish. And in gallium arsenide is much bigger than that. So in some sense, we're taking indeed, we're considering an orbit that spans several cells. So we can consider the microscopic dielectric constant of the medium. So that's consistent. And what's the ionization energy? The ionization energy changes much more. We have a change which goes in the opposite direction. This was bigger. This will become much smaller. We have a mass now in the numerator. So if we take a mass of about a tenth, we go down to about an electron volts, but now we have the dielectric constant which enters with the square. So we get another 2 orders of magnitude. So essentially we expect that the Rydberg in a solid will be about a factor of 1,000 smaller than this. So rather than 10 eV, we expect energies, ionization energies of the order of 10 millielectron volts. So that's good. That's what I wrote here. And that indeed tells us that this number is smaller than KT at 300 Kelvin, room temperature. So indeed, ionized impurities of this type, hydrogen-like, are expected to give us, to dope the material, because the electron is going to be free. Clearly, there are impurities, traps like oxygen, carbon in silicon, for example, that give deep traps, and that's because they distort the lattice, they distort the bonding configuration, so the potential is not given by a simple ionic hydrogen-like potential. Okay, the final, are there any questions, by the way? Am I still online? Do I exist? Yes? Do I exist? No? Any feedback from anyone, please?
Yeah, we are okay.
We're okay, good. Yeah, I have nightmares occasionally about talking 3 hours to myself.
No.
I mean, probably in 10, 15 years, I'll get to that point naturally, but I'm not quite there yet of talking to myself. I mean, if this COVID situation continues, we'll all be talking to ourselves pretty soon. Okay. So no questions. All right. So here I would like to use this equivalent Hamiltonian equation applied to the envelope in a particular case of a silicon inversion layer. As I said, historically, this was, I think, the first example. In 1960s, I don't know if, when did Leo Ezaki come up with 3.5 stuff? That was in the 70s, right? So it was later at Bell Labs. So I think it was the first example before quantum wells came about. So what we're going to do is, let me give you a picture first of all. We have a silicon inversion layer, which means the potential is the potential, which is, maybe this picture is better, well, whatever, this one. We have the bottom of the conduction band of a silicon. This is a p-type silicon. There is an oxide on this side. I apply a gate bias, which pushes the Fermi level of whatever the gate is down. So I invert silicon. The Fermi level of the silicon p-type substrate now crosses the conduction band, and I invert silicon. That's why I call it inversion, in which the p-type silicon becomes n-type near the silicon-silicon dioxide interface. The fact is that this potential now changes so fast here that I cannot ignore quantization effects, the fact that the electrons will begin to move back and forth here in a quantum fashion. So what I do is I go back to the envelope wave function approximation for the Schrödinger equation. This is, by the way, work that was done by Frank Stern in, I think, in 1964 and 66, 67, there were other papers. In silicon, I have a little bit of a problem. I remind you that, as I said before, equi-energy surface in near the minima, the 6 minima of the conduction band in silicon are rugby balls. They're not spherical. They are ellipsoidal revolution. So the effective mass tensor is diagonal, but I have two different masses. The mass along the cross-section, which is circular, of the football, which are the transverse mass, and they go along two directions, and then the larger mass, which is along the longer axis of my ellipsoid, longitudinal mass. If I have the silicon-silicon dioxide interface along the XY plane, so I consider the Z direction and the direction along which there is confinement, and I want to solve this equation, then I have to consider two possibilities. Either the ellipsoids, in which along the Z direction I have the longitudinal mass, and there will be two of them, which are aligned along the Z-axis. And then I have the other four, in which I have the transverse mass along the Z direction. So I will have to solve Schrödinger equation twice, this Schrödinger-like equation twice, once using the effective mass, which is along the longitudinal axis. And that will give me a set of twofold degenerate eigenvalues. And then I have a set of fourfold degenerate eigenvalues with a mass, which is the perpendicular, the transverse mass. The idea indeed is to expand the wave function that I want to solve as plane waves on the XY plane, and then whatever is the unknown along the Z direction, which is, let's call it the quantization direction. And then I have to solve this equation in which I then separated the variables. The total energy will be the energy along the Z direction, which is called E over here, plus the kinetic energy of the motion of the electrons along the XY plane that I have ignored. And the wave function along the Z direction satisfies this equation, having separated variables, where this mass, well, I should say, as long as the Z direction is along one of the principal axes in K-space, the 1, 0, 0 direction. Otherwise, I can transform the coordinates, the variables in another way. It's a little more complicated. I'm not going to discuss that. There is an extra phase that I have to deal with. So I get two sets of equations, if you want, both of them of this form, but this mass m sub z will be either the longitudinal or the transverse mass. In addition to that, I don't know what the potential is. The potential will be the solution of Poisson equation, in which I have holes, which in principle I may have, particularly important as I move away from the interface, so not so important in inversion layer, and indeed we can use a depletion approximation if you wish and ignore it. But then I have the charge of the dopants. We said that it is p-type, this is the bottom silicon, so there will be a negative charge of the dopants, and then the density of the electrons. This is the tricky part, because the density of the electrons depends on their spatial distribution, which in turn depends on the square of the wave function along the Z direction. The distribution of the electrons in a plane is constant because the square of the wave function is independent of the coordinate r. These big bold uppercase symbols are variables in the xy plane, I should have said so. Okay, so using the translational symmetry, my potential will not depend on the coordinate r, essentially because I'm assuming that the dopant is uniform in the xy plane and the electron charge density is also uniform because of this dependence as a plane wave. So I can separate variables and find that indeed the potential depends only on the coordinate z. So what I have is a set of two differential equations, coupled, linearly coupled, and well, not linearly actually, because it's a little more complicated. And the main problem will be to couple this equation via the density of the electrons. Again, the electron density will be the square of the wave function zeta, but I have to consider all electrons up to the Fermi level that I have. So that would be a little bit of a complication. Holes, this is something that I think most of you have seen already. We can assume that holes can be described by their bulk distribution, and that's because they're far away from the interface, so there are no quantization effects. I hope you're familiar with this. The density of the holes is essentially the integral over all states which are occupied. So it will be the, oops, I'm missing a parenthesis here, a little bit washed out, is the Fermi-Dirac distribution of the holes. so flipped upside down if you look at the usual band structure, times the density of states. And the density of states, if I'm assuming parabolic isotropic valence band, none of which is true, but let's ignore it, and define some effective mass, which is a reasonable approximation of the approximation I'm making, then this will be just the integral over the energy of the density of states times the probability that a state is occupied. And you can expand this in this form. And this object is what's called the Fermi-Dirac integral of order 1/2, which is given by this symbol. Actually, I never remember what, I think this 2 over square root of pi is part of the definition, so that I get exactly the exponential in the non-degenerate limit. I hope you're familiar with this. If not, ask me, and we can discuss it a little bit. These integrals cannot be evaluated analytically, unfortunately, only in some particular cases with this integer, with this index is an integer. In general, they've been studied a lot. They have series expansion, asymptotic expansions, sometimes calculated numerically. The derivatives are also important to calculate screening effects, for example. But we can describe the holes in this simple way, and then in the non-degenerate limit, they become simply, as I said, this object becomes just an exponential, which is Boltzmann statistics, and then you can describe holes in a simple way, essentially, which is the number of holes that you have at a given position is the exponential of the distance of the Fermi level from the potential, the top of the valence band at that point. For electrons, things are a little more complicated, simpler in a way, more complicated in another. Simpler because you can actually calculate analytically the electron density as a function of Fermi level in 2D. That's quite simple. And that's because you get exactly the same expression that we had before. Some differences because we're working in 2 dimensions, but this integral now does not have a fractional power of x. Actually, it doesn't have x at all. It's just a constant. And so that you can do the integration analytically. And you find that the total number of electrons as a function of Fermi level will be just this object, this evaluation of this integral, which is given by this expression, where E mu is the subband index. The total number of electrons that you have now will be the total number of electrons that you have in a given eigenlevel, eigenvector of this equation. This equation will have many eigenvalues, which are essentially these levels that you have in the notch of the potential. Oops, where am I? Here, finally. So this will be the number of electrons that you have. You see that you have a summation over the various eigenvalues, and this is the difference in energy between the Fermi level and the eigenvalue that you have. Each of them is called a subband. There are electrons which are moving in 2 dimensions, and this is the total number of electrons that you have up to the Fermi level in each subband. Having found what this is, you have to multiply by the square of the wave function that is given by the solution of this equation. So now you see that these 2 equations are coupled. The density depends on the wave function, but the density fixes the potential, and the potential enters the Schrödinger equation that determines the wave function. So the problem has to be solved self-consistently. And typically one uses an iterative procedure. You start with some guess. The typical guess would be the depletion approximation. You know what that is, so you can approximate your potential with the depletion approximation. You solve Schrödinger equation. You find these wave functions that are zooming in this region here. You see how they go. There is a ground state, a first excited state, and so on. Having found these wave functions, you can calculate the density by plugging these wave functions into this expression. You solve Poisson equation, oops, over here. You plug the potential into Schrödinger equation. You solve Schrödinger equation again, and you keep going. Strictly speaking, if you do it the way I described, the problem will, your computation will never converge because of big noise on this potential. There are under relaxation methods that one can use to slow down, but at least slow down the convergence, but at least obtain convergence into this method. And this was done by Frank Stern for the first time in mid-60s and then developed later on. There are some issues that I'll leave. There may be some things that one may wonder about. This potential, if I show you here the numerical solution, for example, this potential changes quite a bit over a unit cell. So can you justify this expression? You're ignoring some effects that we saw were important. Exchange and correlation, for example. This is a single electron approximation, but we have many electrons. In principle, there are exchange and correlation energy effects. So these are things that have been discussed in the literature. The fact that the potential changes fast actually can be justified. Exchange and correlation, no, you have to add it in some way. This has not been considered here. Strangely, it so happens that correlation doesn't matter too much. Exchange cancels almost exactly the image charge effects that you have that are also ignored here at the silicon-silicon dioxide interface. We use over here, where am I? Over here, where am I? This epsilon, actually we have to account for some corrections which are caused by the fact that you have a discontinuity of epsilon between silicon and silicon dioxide. So in principle, this potential has to see also the image charges at the other side of the interface. They kind of cancel the exchange effects for some funny reason for the prime and prime value anyway. And you see here in this picture, the solid wave functions are the wave functions that you have obtained by solving Schrödinger equation with a longitudinal mass along the z direction. Historically, these are called unprimed ladder or unprimed eigenvalues, simply because the other guys, the wave functions that have been obtained by solving the Schrödinger equation with the transverse mass along the z direction, have been called primed, I think by Frank Stern. And you see both ladders here and the wave functions that you have. And here I think I showed the total classical charge density that you have and the quantum mechanically charged density. So this is the, I would say, the canonical example on how to use the effective Hamiltonian or equivalent Hamiltonian or envelope approximation of Kohn-Latinger equation, whatever you want to call it, effective mass equation, in a particular case which is of technological interest. Of course, these effects are important in devices because the fact that the ground state is not down here, but it's shifted by significant amount. I think this was for a charge density of 10 to the 13 electrons per square centimeter, which is about a field of 0.7 megavolts per centimeter. And silicon, this is a significant shift, about 0.3 eV, which is a shift in a threshold that you would have on your transistor if you didn't account for quantum size effects. Okay, exactly an hour and a half. Let me just conclude before we take a few minutes break. Extending to heterostructure, I was debated whether I should spend a lot of time discussing it or not. I'll give you a flavor for the complications that you have. I'll show you in the next hour an exact solution of the problem using empirical pseudopotential. But if you don't want to go there, which is computationally expensive, people have considered heterostructures. For example, indium gallium arsenide quantum wells. There you have, in this particular case, we decided arbitrarily that the barrier between silicon and silicon dioxide is so tall, it's about 3 volts, 3.2 volts, that we can assume that the wave function vanishes here. So in solving our Schrödinger equation here, we're assuming that zeta of z equals 0 is equal to 0. And indeed, it's not exactly correct, but the errors are tiny. When you deal with a barrier such as you would have in a indium gallium arsenide quantum well, the discontinuity between the indium gallium arsenide and the gallium arsenide conduction bands is very small. In general, in 3-5 heterostructures, you have discontinuities of 1/10 of an electron volt or a few tenths of an electron volt. this is not large enough to justify a same approximation, that the wave function vanishes at the hetero interface. So you have to consider what happens to the wave function as you move from material A to material B. So if you move from a material at the left to a material at the right. And typically what people do is, of course, you have continuity of the wave function, and then you impose continuity of the flux, probability flux, which is the derivatives have to be continuous, but the derivative is divided by the mass in each region. This gives you the velocity, essentially, of the probability flux. The problem is that this is not the wave function. If you're using a simple Schrödinger equation as we did here, with the second derivative, this is only the first term of the expansion of the operator E of k, and we're assuming only the envelope. So what happens to the periodic component of the wave function? And what happens when the dispersions are non-parabolic? In indium gallium arsenide, for example, the non-parabolic corrections are extremely important. They're very quick. For example, the mass increases by a factor of 2 within the first tenth and a half of an electron volt as you move up from the bottom of the conduction band. So this has led to, from the first proposal, I think it was Bastard who proposed it for the first time for heterostructure. Bert has published lots of papers dealing with how to justify these two assumptions. Let me just say that in practice it works. Ignoring the periodic component of the wave function is a relatively good approximation for this particular matching conditions. Non-parabolic corrections can be accounted for quasi-analytically. Again, there are situations that we will deal with in which the periodic component of the block function, the little u's, are extremely important. Overlap integrals and optical transitions in particular. They cannot be ignored. So I need a little bit of a break to get my espresso and clear my voice. So I guess we can resume in 10 minutes if everybody's okay with it. Good. So I'll see you in about 10 minutes, say at 12:02.
Okay.
Good.
See you later.
Thank you. Pardon me? You say anything, Giorgio?
Yes, I said I'll see you later.
I'll see you later. Okay. Arrivederci. Arrivederci.
Arrivederci. Dopo un'ora e mezzo
Massimo, I have a question for you.
What?
I have a question for you.
Oh no, another one. Another week worth of work now. Okay, let's hear it. Shoot it. What's the question?
Oh, can I go? Can I go? Okay. No,
Go,
the
go.
question is rather precise. I mean, I mean, when you talked about the pseudo-potential method, and even in this case, when you are using where you're solving the Schrödinger equation in the inversion layers, what is the impact of the exchange and correlation terms of the energy which has been dropped? I mean, we have talked about exchange correlation terms, talking about pseudo-potential and everything, and then you said when you build the ion potentials, then everything is plugged in there, the exchange and correlation. But what about the exchange and correlation terms for the valence electrons, the ones for you want to solve the band structure for? Okay?
Yes, okay.
And
so
what is the importance in the inversion layers? Because I'm not very clear about that.
So I'm sorry if I wasn't clear. This is not what I showed. Let me show the slides again. Where am I? Where am I? Let me show the slides again. Here you go. Okay. So you see the slides? Yes. This approach is effective mass. It's not pseudo-potential. And you're absolutely right. Where is it? This term here has been obtained by some other ways, right? So if you want to be rigorous about it, the effective mass that we're defining here has been obtained by expanding the dispersion that we've calculated using DFT, whatever you want, that accounts already for exchange and correlation of the valence electrons in a crystal. Good?
Yes.
Yes. Now we are dealing with conduction electrons, free carriers. So the exchange and correlation terms that I mentioned before are those for the free electrons only.
Okay.
The valence electrons is already been lumped here somehow. Now we have to deal, in addition to this potential here that we obtained from Poisson equation, we would have to add extra terms to this object that enters here. And these are the exchange and correlation terms that I was talking about. So there is, I'm not sure if it is the original physical review letters by Frank Stern, or if it's in another paper. Definitely it is discussed in the Ando Fowler Stern paper, the Review of Modern Physics 1982, I think, what I call the Bible for the two-dimensional electron gas. They deal with the exchange correlation terms that you have to add to this piece, and also the image force correction.
Oh, okay.
Okay, and so what happens is that the correlation is relatively small, and that's because the densities are not too high. The exchange is important instead, but it's almost exactly canceled by the image force correction. They go in opposite direction. I can probably dig out the plot that they have. I'll send you the reference. They show in a plot what happens when you add one term only, both terms, and so on. And when you add them both, you go back to what you have when you don't add anything, roughly. Is it clearer than it was before?
Yeah, I think so. So essentially, you have, in principle, to include in the potential term.
Yes, you do. Okay. The fact is that if you don't, you get a better result than when you add only one of the two terms.
Okay.
If you add only exchange, I think the energy goes down because you reduce the Coulomb repulsion. If you add the image correction, the eigenvalues go up. If you add them both, they don't change much from what you have by not doing anything. Ignorance is a bliss. So if you don't know that all of these corrections exist, you actually end up with a better result than if you do and you add only one of them. So there are two exchange and correlation pieces. One is already included here somehow.
Yes, yes.
And that's for the valence electrons and core, whatever you want to add.
Yeah, for the core.
The other one is for the free carriers that we're dealing with here. These guys characterized by these wave functions. And those go the way I told you. So I'll tell you the reference, but definitely in the Review of Modern Physics paper, they talk about it. And they show a plot in which they show this stuff.
Okay, thank you.
Good. Okay, so now I want to review a little bit what we have done, and I want to touch upon the problem that we already mentioned. Let's go back to what we were doing with pseudopotentials, plane wave methods for a crystal, how to calculate the band structure. What do I do when I have a system which is not periodic in 3 dimensions? A nanowire, a quantum well, a thin silicon body, ultra UTB, SOI, for example. How do I get the band structure for those systems? It's extremely important to do it. For example, one problem that has been used a lot, this procedure that I will describe, been used a lot, is to calculate what happens when I reduce the dimensionality of an indirect gap semiconductor and I obtain a direct gap, which is indeed what silicon does, what germanium does. And germanium lasers, for example, people try to build them by converting germanium from an indirect gap material to a direct gap material. Germanium is easier because the gamma valley has an energy which is not too different from the satellite valleys. So it takes a little bit of strain or quantization to induce this effect. So this again, it was a tutorial that I gave, I think in 2013. I remind you what we're dealing with now. So this is the equation, the same equation that we started off with several lectures ago. I forget when exactly. The full Hamiltonian of the lattice with the electron contribution, kinetic energy, Coulomb interaction on the electrons, the ionic kinetic energy, the interaction among the ions, and then the interaction between the electrons and the ions, and how we dealt with the problem by using the Born-Oppenheimer approximation. First, by decoupling the electronic component for the ionic component, by taking this term, by adding a 0 here. So looking at the position of the ions at equilibrium. And so for the first, the second, and the last term become our ionic electronic Hamiltonian. This we'll be dealing with later, describing phonons and so on. Then we went into having extracted, thanks to the adiabatic approximation, that I remind you relies on the observation that the ions are much heavier than the electrons, so they move much more slowly, they're sluggish. So we can consider the motion of the ions here as a parameter, the position of the ions as a parameter, so that we don't have to look at the full dynamics of the ions when dealing with the band structure of the electronic excitation. Of course, the issue of dealing with electron-phonon interaction, we rely on this, so we'll have to deal with it eventually. Then we went to considering the wave function expressed in terms of a Slater determinant, and then writing single electron effective Hamiltonians or Schrödinger equations by minimizing the energy when we consider the mean field generated by all of the other electrons. So we had an equation in which the kinetic energy of the electron is represented by this term, the lattice potential is represented by this term, and which is the potential of the ions, the cores. And then we have a Coulomb repulsion among the various electrons, which is a term which is positive because it's a repulsion. And you're simply considering the effect of the charge of all of the other electrons again, remind you that this should be a factor of 1/2 or just excluding double counting these pairs of electrons. And so this is just the mean field that a single electron I sees as due to all of the other electrons J, which are distributed in the crystal. You can do better than the Hartree approximation, which is what this approximation is called, by adding an exchange term, which is by swapping the indices I and J in this term. This is a term which now becomes attractive because the Coulomb interaction, the Coulomb repulsion is reduced. So this is what we were dealing with. And then we decided that this complicated terms over here, well, this is the Hartree term. This term is something that we cannot deal with the Hartree-Fock approximation. It's too complicated in a lattice. So we relied on the Oelenberg-Kohn and Kohn-Sham theorems. The first tells us that this messy term, which accounts for the exchange and correlation terms, which are those that we just discussed with Professor Gnudi, they can be represented only as a functional of the density because of the theorem that Oelenberg-Kohn proved that the ground state properties of an electronic system depend only on the charge density. This is extremely useful. In principle, it can depend on many other effects on the wave function themselves, on the phases of the wave functions. They do not, as long as we stick to the ground state. This theorem is useful, but doesn't tell us what is the form of this function. It depends only on the charge density, but we don't know how. And so the first approximation is the local density approximation, which says we can use the same functional that we have for the homogeneous electron gas, assuming that the electron density doesn't change too fast spatially in a lattice. This sort of works. It works very well for the valence band. It works very well for the atomic structure. It doesn't, not surprisingly, it doesn't work well for the conduction band. It gives the wrong gap because, after all, the Oelenberg-Kohn theorems tell us that there are two theorems actually, it's lumped into one, but they tell us that this is true, that the ground state properties only are determined by the charge density, not the excited states. And there have been a lot of empirical and not approaches to deal with the problem of the band gap problem that you get in DFT. So this is where we started from. And again, the local density approximation tells us that this exchange and correlation potential is proportional to the cubic root of the density there at that particular point. That's why local. Then we saw that we can approximate or we can reduce the complexity of the problem by looking not at this potential as including also the ionic singularities. The Coulomb potential had the singularities at the position of the ions. This would require us to solve the problem also for all of the core states. And really we don't need them because we're interested in the bonding configuration of the crystal, and it's a lot of effort computationally. So that where comes the idea of pseudopotentials, in which we chop the singularities by using either a model potential or a pseudopotential, and we describe the two approaches which boil down to the same one, so that we can reduce the complexity of the problem by requiring a smaller number of plane waves. In principle, if we keep the cores, then the spatial variation of the potential, the lattice potential, is so fast that we need many plane waves, many G vectors, in order to represent this fast variation. If we smear out this singularity somehow, then we reduce the number of plane waves that we need, and then we can deal with the eigenvalue problem, which is a matrix of a much smaller rank. And this is what we discussed. So this is an overview of what we've been dealing with in the past. Now, in concrete, for example, the empirical method, again, self-consistent means the lattice potential or the pseudo potential that we calculate this object here has to be calibrated by starting from an isolated ion and calculating the Hartree-Fock spectrum of that ion, and then looking for the pseudopotential that gives us the same spectrum of the isolated ion, which means that we have to include exchange correlation and the Hartree component when we do the calculation. Empirical means I lump all of these effects, Hartree, exchange correlation, into this model potential that gives me the correct band structure for a particular configuration. The advantage of the pseudopotential when we use it self-consistently is that it's portable. I can use the silicon pseudopotential when I want to deal with silicon germanium alloys, with silicon carbide, whatever. But I need to do a lot of calculations. The empirical has the advantage that I don't have to do, don't have to calculate a self-consistent problem, but it's not portable. So silicon in silicon, or the pseudopotential of silicon in silicon carbide or silicon germanium will be different in principle. And several models have been proposed for these empirical pseudopotentials. For silicon, I show here some forms. One that is used for group 4 materials is this particular expression, which is given here, is shown here. This decay at large wavelength, at short wavelengths, which is indeed what we need going to the pseudized problem is given by this hyperbolic tangent term that we can tweak. There are terms that we can also use to get the right work function of the material. Professor Zunger's group has given instead pseudopotentials, empirical pseudopotentials, which are sums of Gaussians. And this term over here has the same effect of chopping off the high frequency components and also giving the right work function. In many situations, we will need hydrogen. What I want to do next is to show what we can do when we want to calculate, for example, the band structure of a thin silicon slab or a nanowire, which means we start from bulk silicon, but then we cut the crystal at two places with two parallel planes, and we remove all of the ions which belong to the upper half and lower half plane, and we're left with a silicon slab. The problem is that we have dangling bonds. Clearly, we have removed the ions from a particular region of space. In a nanowire, we remove them all around the wire. What happens to the silicon ions, which now are not coordinated anymore with anything because we removed those ions? So a typical trick in numerical calculations is to introduce a passivating object, an ion, which typically is hydrogen. For silicon, it works very well. For germanium, it doesn't work that well. It's a matter of physics here, not just numerics. Germanium is not easily passivated. For 3,5s, there are tricks that Professor Zunger's group have developed to introduce passivating layers to do the same things. So fictitious materials which have the simple scope of removing these dangling bonds, which give additional bands in states in a gap, physically reasonable. So these are typical expressions that people use to do calculations of band structure of solids with empirical pseudopotentials. So again, this is a little bit of a summary of what I said before, the advantages and disadvantages of DFT and empirical pseudopotentials. Tight binding, I have my own questions about tight binding and empirical formulation that I've discussed briefly before. So you can see the slide also in the recording, and I think I posted them on the class material, so you can look at it. I want to mention that even some 30 years ago, I think, Professor Zunger's group actually simulated quantum dots, pyramid-shaped indium arsenide quantum dots with 1 million atoms. So empirical pseudopotentials, if suitably tweaked from a numerical point of view. Oh boy, now we have to go through 12 beats on my clock, okay? So while DFT is still today limited to, say, 1,000 atoms, but there is really a tall order to simulate 1,000 atoms of DFT. Empirical pseudopotential are more manageable. In particular, today that we're interested in interfaces or layer structures. With DFT, it's complicated because we really need lots of atoms. Think about dealing with an interface in which the lattice constants of the two materials that we want to interface are not commensurate. We have to either strain them, and if the lattice mismatch is too large, the strain will be unrealistically high. In practice, the material will just fall apart, will break with dislocation, stacking faults being generated. So the problem is really still, in many cases, interesting systems are still a little bit beyond what DFT can do. With empirical pseudopotential, you can study much bigger systems, although with the problems that you have to worry about relaxations. I'll give you some examples. So it's not fully predictive in atomic relaxation. I should say it's not predictive. Okay, so this was the situation for silicon. This is the same slide that I showed before, showing the cubic cells, the primitive cells, and the primitive cells in reciprocal space, which are the Brillouin zones. And this is the results that you get with empirical pseudopotentials, local and non-local, compared to the tight binding model. What do you do now? Let's suppose that I really want to study a system of thin bodies. So A is my silicon slab. It's a two-dimensional slab. This is the dimension, I call it Z, the outer plane direction. And I want to study the band structure of a thin silicon layer surrounded by some material B. Could be vacuum, could be something else. I could consider structures which now lack periodicity in two directions. In this case, I'm missing periodicity in this direction. Here, if A is a square cross-section nanowire, some material, I'm missing periodicity in two directions. So what do I do if I want to use plane waves? If I want to use VASP or quantum espresso, or if I want to use empirical pseudopotentials? So the idea is to introduce a fictitious periodicity in the missing direction. So instead of considering a single silicon slab, now I consider a periodic array, AAA, of slabs, discontinuous forever to the left and to the right, surrounded or intercalated with vacuum, with silicon dioxide, with whatever I have. So I introduce this fictitious periodicity in one direction. Here I do exactly the same. This medium here may be vacuum, maybe some insulator, maybe whatever, but I reproduce now, I create a periodic structure by replicating fictitiously my nanowire now in two directions in this cubic crystal. So in red here, the region between the two red dotted dashed lines, now is a supercell. The supercell will be composed by the regular cell that I have, the cubic cell that I have for my bulk material in the XY plane, but then it would be extended along this direction by this amount, so that I can recover periodicity in 3 dimensions. Here is the same situation. The square, which is contained by limited by the dashed red line, is a supercell, which is fictitious in 2 directions, while in a direction in the plane of the slide will be the usual periodicity, the lattice periodicity of my wire, which will be whatever periodicity is dictated by the wire that I'm considering. 100, 110, 111, they will all have different periodicity, but it will be with a lattice periodicity in the plane direction, and the on plane instead, on the plane, will be a fictitious periodicity. I pay a price. I pay a price, and let's remind you why. Remember that the number of plane waves that I need is determined by the fact that I have to define vectors, which are the primitive translation vectors in reciprocal space, the G vectors, and they have to fill the sphere inside the cutoff energy, which is the energy beyond which the off-diagonal terms of my matrix, or the pseudo-potential, are much smaller than the diagonal, which is the kinetic energy. Now, if I make the lattice constant larger, this is not the lattice constant of the material, it's much bigger. This distance is not the lattice constant of the material, it's much bigger. It has to be bigger because if I make it very close by, then there will be, let's say, tunneling of the wave functions between two wires or between two films, and I want to decouple these films. So this distance has to be sufficiently large so that up to the energy, maximum energy that I'm interested in, the wave function will decay exponentially so that the wave function of this lab will be zero in this lab. So there will be no crosstalk. Typically, I need distances of more than a nanometer, a few cells, a couple, 3, 4, 5 cells. So this distance will be much bigger. This A will be much bigger, which means that the G vectors that I have are very many. They're smaller. They're separated by a smaller distance. So when I want to fill my sphere in K-space up to the cutoff energy, I will have lots of wave vectors. For example, in silicon, in bulk silicon, using empirical pseudopotential, I get a very good band structure when I use about 100, 120. I apologize, my Siri on the phone. Okay, so I have a much bigger number of G vectors now that I have to consider, which means that the rank of the eigenvalue problem that I have to solve now, rather than being 100, it might be 100 times bigger. For a 111 silicon nanowire, for example, for empirical pseudopotential with the same cutoff energy, I need about 14,000. It's doable. It's not impossible to do it. You can also do it on a laptop today for structures which are more complicated than that, bigger structures and so on. Then, of course, this number grows and you approach the situation, the cases in which you cannot deal with it anymore. So there are some limits. So you can recover periodicity in 3 dimensions at the price, and the price is an increased rank of your supercell. So what do you do to simulate the electronic structure in these cases? And here is an interesting example that I show. I want to simulate, for example, with empirical pseudopotentials, the same system that we saw before at the end of the previous lecture at 10:30 or whatever it was your time, 5:30 I guess, which was adding an external potential to my problem. So what I do here is essentially something which reminds us of the equivalent Hamiltonian formulation. I'm looking at the wave function expanded into envelopes of my block functions. I have these first 2 terms. So if I didn't have this term phi, I would have exactly the band structure problem, except that the G vectors now are different. They're the G vectors of my supercell. In addition, I add the potential, an external potential, which is the confining potential in my inversion layer, for example. And this is just its Fourier transform, which is, again, reproduced periodically in a fictitious way, exactly the same fictitious periodicity that I've had to deal with a supercell. So I can actually study the system using, I'm saying empirical pseudopotential. In principle, nothing prevents me from using DFT in this case, with the addition of an external potential, which I replicate periodically in a fictitious way. And these are the expressions. So if I have, for example, the potential in an inversion layer, this will be the depletion potential. Its Fourier transform will be just given by this term. Similarly, if I have a gate all around silicon nanowire, I can consider the potential induced by the gate by taking its 2-dimensional Fourier transform. There's no restriction of what the potential looks like, except for the fact that If the potential varies very fast as a function of space, then these Fourier components do not die fast enough at short wavelengths. And so the rank of the problem that I would have to solve increases. This may actually go remain larger more than what the lattice potential does. But in principle, there's no limitation. I can study tunneling, I can study all sorts of effects by using this supercell trick. Okay. I'm assuming so far that the structure is periodic, no transport. I can in principle go to open boundary conditions. I may discuss it later on in the course in a few next weeks or months, what happens when I apply open boundary conditions to this system and solve this problem, which will be a full quantum transport problem using empirical pseudopotentials. The system is complicated, clearly. It's the rank of the matrix is very large, as I said, because the number of G vectors is bigger, because of the fictitious periodicities I had to introduce, particularly for structures which are one-dimensional, such as nanowires. And also because the external potential may be varying quite fast, and then I need to retain many Fourier components also for large values of the Fourier components G. This is an example of a thin silicon film, a few cells thick. This is just 9 cells of silicon, 9 cubic cells, so 4.5 nanometers roughly. It's separated by 2 vacuum cells, so about a nanometer of vacuum. And what you see are the unprimed eigenstates or subbands that you have, which are those that you get when the longitudinal mass is along the quantization direction. And these are the states which you have for the prime subbands. There is a little shift, of course, the scale is very large between the two. And you see also the quantization of holes. More interesting is to see the square wave functions in the various states. You see the envelope, but you also see these wiggles. And these wiggles are the block, the periodic components of the block functions. Here you see the unprimed. The numerical issues here are tricky. So you see still the envelope. It's quite noisy also because the ions are, the average over the ions is a little more difficult. And you also see the same thing for holes. Also holes which are quantized. You see the heavy holes, the light holes, and the split off holes, and there are various bands. In this case, the problem has been solved non-self-consistently. What I have here is an infinite barrier, so that the wave function is forced to be 0 here. This will be my boundary condition, and it's a triangular well approximation. And you see here the density of states, and zooming in a conduction band, you see what you get from the parabolic band approximations. These are the various density of states that you get, and this is what you get using empirical pseudopotentials. This does not deal with the problem that I mentioned before, which is what happens at the interface, the hetero interface between two materials. And this is indeed an interesting problem. It was a set of devices that we were interested in some contract in the past, in which we had essentially indium gallium arsenide channels with an indium phosphide buffer layer, and then an indium aluminum arsenide insulator, so to speak. And there were N-channel 3,5 FETs. So this was the structure, or lattice matched to indium phosphide. They were built by Mark Rodwell at UC Santa Barbara. And if you do empirical pseudopotential calculation of these systems, you replicate periodically this cell. This is your cell. It's beginning to be quite large in this direction. You see the wave functions. They are displaced by the energy at which they happen. And you see how you get the penetration of the wave functions inside the barriers. This is for an inversion, for inversion layer when you apply positive gate bias. You also see the hole states. Here for flat band situation. And this you see when you apply a negative gate bias, so you have a P channel in this particular case. So this solves the problem of matching the wave function, which has been a problem studied by dozens and dozens of papers in the literature, how to match the wave functions. Notice also how at some point you get free electrons, essentially. You see electrons over here, which are essentially localized into these inversion layers, but at some point you reach the energy or the work function of the medium, and so the electrons become delocalized. They're free electrons, so to speak. The pseudopotentials that I used are those used by Professor Zunger's group. Some virtues of the empirical pseudopotentials that you do not get from the effective mass approximation is this structure is extremely complicated in the prime values. You also see that these states are doubly degenerate and they're split a little bit. And this is an effect of value splitting, which has been studied theoretically, and you don't get it from using the effective mass approximation. Again, the wave function matching that you have. Graphene. You can study graphene exactly in the same way. Graphene, as you know, is an hexagonal lattice. The Brillouin zone is also hexagonal. The two-dimensional Brillouin zone of an hexagonal lattice is also hexagonal. The lattice of graphene is supposed to, it can be viewed as the combination of two sublattices, triangular sublattices of the carbon atoms. And this, probably you know already, is the band structure that you get near the minima of the conduction bands and top of the valence band. They touch, and they look like two Dirac cones. We'll talk about it later. I'm afraid not today, but next week. And this is the band structure. I think this is a tight binding calculation. You can calculate it using supercells and empirical pseudopotentials. There is an amazing pseudopotential, which actually we have used extensively. The group of Professor Kurokawa in Japan in 2000 proposed some empirical pseudopotential for carbon that works amazingly well, both for the sp3 bonding configuration that you have in diamond and in the sp2 configuration that they calibrated. This transpolyacetylene, I'm not a chemist, but this is essentially, it's what I would call a 2-AGNR, an armature graphene nanoribbons with a width of 2 atomic layer. It's a polymer plastic. It's amazing that it works so well in both configurations because I told you that empirical pseudopotentials are not portable. You have already lumped inside the empirical part of the pseudopotential the Hartree potential of the valence electrons. sp3 and sp2 configuration coordination are very different. And yet these pseudopotentials give amazingly good results in both cases. A French group by Professor Meyer published a little bit later a single electron Hamiltonian calibrated to graphene. Single electron means you can only expect one band, not more than that. And you see the results that you get from the Kurokawa and the Meyer pseudopotential for graphene. And here is your Dirac point. It works remarkably well, the Kurokawa pseudopotential, except for a band in the conduction state that gives a little bit of artifacts when you go very thin, very narrow diameter nanotubes or very thin graphene nanoribbons. And this is the density of states that you see, and this is the Dirac point. These are nanowires instead. We're considering a band structure of silicon nanowires. I will go fast here. This is just for your information. Of course, I will not ask question in the exam about this stuff. And you see the ballistic conductance that you can calculate. So the supercell trick is extremely useful to reduce or reformulate a non-periodic problem into a periodic problem. You pay a price, but you can really approach a number of problems which is remarkably interesting. One thing that I should mention is, for example, in this case, if I want to study capture of a free electron in a quantum well, the wave function that I get for the two-dimensional quantizations, they're three-dimensional wave functions. The only thing is that their energy does not depend on a k vector in a perpendicular direction. But if you go to energies which are large enough, then you begin to see a dependence because the electrons become free. So the capture of an electron in a quantum well, which is interesting, for example, in lasers, where you want to know when in a junction laser, quantum cascade laser, for example, when an electron which is free injected from one contact is captured in the well. The problem is always a little tricky to do with effective masses because you have to calculate an overlap integral between a three-dimensional wave function and two-dimensional wave functions, which requires the introduction of some normalization length, which is always a little bit tricky. Instead, in this case, you can study the problem rigorously, so to speak, if you accept the pseudopotential formulation, empirical. Okay, you can see nanowires. One interesting thing about nanowires, for example, this is circular cross-section nanowires. What I want to show is some drawback of empirical pseudopotential. This is a bulk silicon, and then I've cut it in a circular cross-section. These little smaller ions are the hydrogen terminations, and I can study it. So this is the cross-section. This is view from the top, for example. And of course, this is the structure undistorted. If you did DFT calculation and you relax the structure, then you see how at the edges, the atoms relax. Clearly, these atoms are missing the bonds with the atoms which have been cut out when we formed the nanowire. So there is a relaxation. Is it important? Well, you see here the differences. Unfortunately, the scales of the energy are a little bit different, but you see that if you use fully relaxed, or if you use DFT calculations but without relaxing and relaxing, you see some differences in a conduction band. So it is something to keep in mind. The gap changes and the band structure changes a little bit. From a DFT point of view, this is not a big deal. Unfortunately, we transport people are sensitive to differences of the order of KT. And for DFT, this remains an issue, particularly when you have intervalley or interband processes. DFT does not give you the accuracy, and transport parameters instead can be quite sensitive to that. You can study graphene nanoribbons, and I want to show graphene nanoribbons to show one issue with tight binding. So to grind an axe with tight binding. These are armchair graphene nanoribbons. What you see is the edge. This is the ribbon seen from the top. This is the transport direction, if you wish. We have chopped graphene, cutting it at the edges. These are the armchair edges on one side and this on the other side. These open circles are hydrogen that terminate the dangling bonds of the carbon ions. And typically these are called AGNR, armchair edge graphene nanoribbons. The number in front counts the number of dimer lines that you have, atomic lines that you have. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be a 9 AGNR. And you can study the band structure of these materials. They have been studied and are still object of some interest because graphene is great, but has no gap. I'm not sure if this is my personal opinion, but it has been a little bit of a disappointment. I think the major application of graphene has been tennis shoes and maybe tennis rackets, not much else. But in terms of electronic properties, the absence of a gap is really an issue. If you chop off graphene and cut it into a ribbon, then you do get a gap. So this has some promise. The problem is that you nearly had to cut them precisely, otherwise you get roughness, defects and vacancies or problems, and transport is very sensitive to that, dramatically so. So I'm not holding my breath to seeing the first computers using graphene nanoribbon logic. Anyway, you can calculate the band structure, and the interesting thing is that if you look at the band gap as a function of width, in principle, you say, well, that's a particle in a box. So the narrower the ribbon, Then you have states, which can be standing waves in graphene, nanoribbon. And of course, if the ribbon gets narrower, then clearly the band gap will grow, because essentially it's like a particle in a box. The ground state energy increases for the conduction band and pushes down for the valence bands, and you get a bigger gap. Indeed, that's what you see, but I wouldn't say surprising, but the deviation, the dependence on the gap on the width of the ribbon for armature edge graphene nanoribbons splits into three families, depending on what that number, 9 in this example here, is. What is the width of the ribbon measured in terms of number of atomic lines? And you see that you have ribbons which have a width which is given by a multiple of 3 plus 1, such as 7, such as 10, such as 13, which have a big gap. Instead, if you have a multiple of 3 plus 2, you have a small gap. And the multiple of 3, like the 9 and GNR that I showed here, are somewhere in between. These gaps are actually perhaps underestimated. Calculations using GW, using DFT, local density approximation, and GGA give very similar results. With GW, they give gaps which are about a factor of 2 larger, almost a factor of 2. The problem is that GW sometimes overestimates the gap. For example, for gallium arsenide, I think it gives a band gap of 1.7. It's not a huge overestimation, but it is an overestimation. So the truth is somewhere in between, probably. The real gap is bigger than what I show here. Unfortunately, experimentally, I'm not aware of any good measurement. Typically, you have a mix of ribbons. You need a large area device, you need many ribbons, and then they come in different widths, and then you get some average. So I'm not sure if there is a good experimental verification of this trend. The reason why there is this dependence is a strange and interesting thing, which I may say was known to the chemist already from the 1860s, from when Augustus Kekulé studied aromatic compounds. Edward Clark in 1964 actually published a book showing why you should expect this. The strange thing is that the first papers that I saw talked about strain effects. This is nothing to do with strain. It's due to something completely different. Oh, here you see DFT and an empirical pseudopotential results, very similar. And the comparison between the band structure is also very similar, with some differences I'm not going to spend time on. Running out of voice here. The reason is the following. Let's see if I can show it here. When you have a nanoribbon, in general graphene, what you have in a given, consider an hexagon and a carbon atom in this hexagon. This carbon atom has coordinated 3 coordinations that you see here, but of course there is the pz orbital, which is sticking out, right? Chemists usually draw a double line in one of these legs, and this is a resonant bond. So it can oscillate between 2 bonds. In a given hexagon, if you put a double line here, you can put another double line in a bond which is not the nearest neighbor bond. Otherwise, you would have a carbon atom which is 5-fold coordinated, which cannot be. If you have an hexagon, say this one, which are identified with this red circle, in which the carbon atom has 4-fold coordination with the resonant bond, the next hexagon cannot have the same properties. Otherwise, you would have a carbon atom which is 5-fold coordinated. So Clark, in his 1964 textbook, called this hexagon as happy sextets. And you can have a happy sextet, you can have another one, they cannot be adjacent for the reason that I just said. Otherwise, you would have a 5-fold coordination. So now it becomes a game of topology, if you wish. Depending on the width of the ribbon, here I show a ribbon which is different by one layer, for example. Sorry, the same ribbon. You see that you have three possible configuration of these happy sectors. Note also that if you terminate the bonds at the edge of the ribbon with hydrogen, the carbon at the edge is fourfold coordinated. So the sextet at the edges have to be happy. So this configuration can happen. If I terminate it with hydrogen, this doesn't happen anymore. This doesn't happen anymore. In graphene, infinite graphene, all of these configurations are possible. So you have a resonance, the wave functions, the pi band of the pz orbitals, which is hybridized into a pi band, resonates between all these possible configurations. But if you chop the ribbon now, you have a situation in which, for example, for the 9 AGNR that I showed before, you're stuck with a single configuration because you must have these sextets at the edges with a hydrogen termination shown here, which are happy. If you add one, now you have two possible configurations, which makes it completely different. And if you have a ribbon which has a width of 3p plus 2, you have yet a different possible set of configurations. Now you can go and analyze the energies of these configurations, and you find that indeed the ionization energy changes depending on how many resonance states you have, and this leads to these three different families. This is fully dependent on this property of the happy sectets being forced at the edges. This is why this is true for a hydrogen-terminated graphene nanoribbons. I don't know if this is a uniformly and universally known term. These are aromatic compounds because Clar studied these properties. We started calling it claromaticity or claromatic properties of the ribbons. The main point that I want to make, if you go and look at what tight binding does, if you use empirical tight binding, pz orbital only, something that I will show later on, nearest neighbors only. The nearest neighbor is the key here. You see that nearest neighbor approximation, in which you consider only what happens when a carbon atom sees the nearest carbon atoms and not the other ones, you cannot capture this property. It goes completely wrong. And indeed, empirical tight binding pz orbital nearest neighbors only gives not only the wrong order, but also predicts that one of these, I think the 3p, will be metallic. And instead, the DFT, GW, empirical pseudopotentials, they tell you that no graphene nanoribbons are metallic. Armchair edge. Zigzag is a different story. Zigzag has a different dispersion. Okay, for the nanotubes, you have a similar situation, and I'm not going to talk too much about it. So I want to start here. If there are questions, any questions? So I hope I've shown. No questions? Yes, please. No question, you said?
The microphone. You have shown several wave functions in a triangular well, and all of them look like a sort of a ripple around the envelope wave function.
These guys.
I was wondering why the wave function doesn't go down to 0.
Oh, this is squared and averaged over a cell in XY plane.
Yeah.
I could show a wave function plotted along some particular XY point as a function of Z. These are being averaged over the cell.
I see.
That's why it doesn't go to 0.
Okay.
If I plot it along one particular direction with yes, then I will see it. I'm not sure, and that's a good question, why for holes instead I see it going to 0, even after averaging. For electrons, I do not.
I see.
So this is the average. And the wiggles are exactly where the atoms are.
Okay.
Projected on the plane. Okay. Any other question? Hey, again, there are no stupid questions. I'll give you stupid answers if you wish, but
you never give stupid answers.
well, occasionally I do. Okay, so let me start with, this is fun. Again, for a student's purpose, this is not going to be material that I will ask at the exam. I'm not going to ask you about special relativity or anything. But so what I want to go to is essentially, let me just show you where I'm heading. I'm heading to graphene again. How to write the Hamiltonian of graphene. We saw the ribbon in terms of the Pauli matrices, which in turn is a factorization of the Dirac equation, which is a relativistic equation for electrons in the case of zero mass. Indeed, if you go through a tight binding model of graphene, you find that the solutions are exactly those that you find for neutrinos, for example. And that's why I think you know that if you look at the Brillouin zone of graphene, you have an hexagonal zone, the maximum of the valence band and conduction of and minimum of the conduction band touch at the Dirac cone at 6 points, which are the vertices, and the two addition vertices, I mean, 3 of these vertices, of the 6, are called K point, and the other ones are called K prime. And the equivalent of interpretation that you get from this equation is that the electrons at the K point are the antiparticles of the electrons at the K prime point. And this is all terminology which is coming from the Dirac equation with zero mass. So I want to give you an idea of why people talk about it. Strictly speaking, I also want to show you that indeed the massless Dirac equation is not a term that you find among quantum field theory people or high energy theorists. It's called either the Weil or the Majorana equation, depending on whether you're dealing with particles which are not their own antiparticles or are their own antiparticles. And you might have heard about the search for Majorana fermions in solid state. So another reason why I want to deal with special relativity a little bit is to go into this fact that we said that in order to couple electrons with an electromagnetic field, I add to the momentum the term, the vector potential of the electromagnetic field. And this is coming from the fact that the momentum indeed is not a quantity which is invariant, I should use the term covariant, under transformation going from a reference frame to another, moving at uniform velocity, which is what you would expect from Galilean relativity. Instead, you have to go to something more complicated. So I hope it's fun. I don't know how many students will have seen at least the basic idea of special relativity in the past, but the way I view the problem, which maybe is not totally correct historically, but it's the fact that at the end of the 18th century, there were two big problems. The two big problems are the fact that Maxwell's equations are not invariant under Galilean transformation. The idea of Galilean transformation is that you have F equal ma, very good, which means that F is equal to the mass times the second derivative with respect to time. If I now, as Galileo, I think, said, I do an experiment on terra firma, on dry land, or if I board a boat with smooth sailing, not big waves, on a calm day, and the boat moves at velocity u, uniform velocity, pushed by the wind. If I do my experiments to verify this law, okay, didn't exist, it was not called Newton's law at the time, so that's where my historical inaccuracies enter into play, but he had an idea about this. If I reformulate this expression in a frame in which things are observed by the guy sitting on a boat, expressed in terms of the frame in which things are observed by the person on dry land, you see that the equation is the same, and that's because I have a second derivative with respect to time. So the derivative of the position x prime, which is the position in the boat, I can use this formula, but the first derivative gives me a derivative of the velocity with respect to time. As long as this is constant, it drops out, and I recover the same equation. So F equal ma is invariant under Galilean relativity. Principle of Galilean relativity says two things, or all physical laws, are equivalent when I view them from a particular observation point or from an observation point which is moving at constant velocity with respect to the first one. Now let's go to Maxwell's equation, and that's where problems come out. Let me consider just a wave equation. We know the Maxwell equation that can be recast in free space as the electric field and the magnetic field, each component of them obeying a wave equation. Now let me go from the prime frame, unprime frame to the prime frame. So I'm looking at an electromagnetic wave on dry land, and I'm looking at an electromagnetic wave from the boat. And we can formulate the problem in two different ways. This equation becomes a disaster. Nope, this equation and this equation are not the same. So if I'm doing an electromagnetic experiment on a dock, or if I'm doing the same experiment on a boat, according to what Maxwell says, again, Maxwell came after Galileo didn't know, I should see different things. In particular, what I should see, which is something that is more obvious than this awkward expression, and that's the other way of seeing it, is that if on the dock I see light traveling at some speed, on the boat I should see light traveling at a different speed, which is the speed of light minus the speed of the boat projected along the direction of the propagation of light. And this is not what has been seen historically. And this is the second problem, which is the Murchison and Morley experiment. Light has the same speed regardless of the constant motion and uniform motion that I have. The experiment was done. Again, I think it's idealized a little bit. You do the experiment in January, looking at the star, which is at some particular direction. You look at the same star 6 months later in June. Now the star is on the opposite direction. The speed of the Earth orbiting the sun is going the other way. So you should see two different speeds, c plus v or c minus v, depending on whether you're in June or January. Instead, you always see the same speed. So what do? Maxwell equations are wrong. Newton's equations are wrong. Here there's two choices, or something in between. So Maxwell equations are wrong. The correct equations have yet to be discovered and are invariant under Galilean transformation. However, this is not experimentally correct because of the Murchison and Morley experiment. The second thing is Galilean invariance is valid for mechanics, not electromagnetism. Historically, this is what people thought, and that's where the idea of the ether came about. There is an absolute frame. Only in that frame you see the speed of light. If you move, and only in that frame Maxwell's equations are valid. But if you move away from that frame, the frame in which ether is at rest, then Galilean invariance is not valid. Instead, mechanics is different, and Galilean invariance is valid for mechanics. This was the solution chosen by most people at the time, with the invocation of this ether concept. Sounds a little bit like dark energy and dark matter. The other idea is Galilean invariance is wrong. Newton's equations are wrong. They have to be, discovered. some general invariance that preserves invariance of Maxwell equation, and the new equation of classical mechanics that we have yet to find will be invariant under this general transformation. And of course, we will require that these new equations, yet to be found, merge to Galilean Newton's equation in a limit in which the velocities are small. So again, having to choose between 1 and 2, people choose 2. 1 and 3, people chose option 2. Instead, Einstein followed option 3, which was a little bit of a leap of faith, and that's why he's a genius. The idea was that he said, okay, so the speed of light is constant in all frames, which move at constant velocity with respect to one another. Okay, let's take this as a given fact. Let's not try and explain it. So if you want, I think you swap the logic. This is a given. What conclusion can we draw? What consequences can we derive from this assumption? And we also assume that some form of relativity must be true. All physical laws must look the same, which means I must formulate them mathematically in the same way, with the same equations, regardless of the constant velocity at which the various frames are moving with respect to one another. So this is where the basic idea comes from. And as usual, in hindsight, it's trivial to see what transformations say. So if light travels at the same speed, if I look at the wavefront is given by this equation. If light is emitted by a point at the origin, x, y is equals 0, at time t equals 0, the wavefront will be described by this equation. It's a sphere, x squared plus y squared plus z squared, with a radius given by ct squared, square radius. Okay, c squared, c squared. On the contrary, if and this must be the same regardless. This should be a square. I forgot. Double square. Regardless of whether I'm using the frame xyz or the frame xy, x prime, y prime, z prime that I used before. So this is a little different because immediately it tells you that the transformation of x, y, and z cannot involve simply x, y, y prime, z prime, but must involve also t. And that's a major difference. So in general, we can do a little bit of algebra, saying if this must be true for a homogeneous and isotropic configuration, this wavefront has to be equal to wavefront, they both have to be equal to 0. At most, they can differ by some function, which is a function of the velocity that we're considering as the relative velocity of the two frames. And so the two frames, sorry that I use k and k prime, we're not talking about graphines here, they're reference frames. I don't know German, maybe someone knows why it's called K in German. Frame of reference, must be a reason. Anyway, the only way that can be is that u and minus u give the same expression, so that, which means that 1 over L must be equal to L, which means that lambda must be equal to 1. So we come that this equation, with this is 1 now, and again, CT is all in parentheses, I forgot to put it there. The only way we can verify this is that if time, which I call now x0 is CT, if time and space are mixed, okay, I can verify that this is true. I encourage you to do it, to prove analytically, if this is the transformation that is required, where beta is the ratio of the velocity, relative velocity of two frames to the speed of light, and gamma in this particular factor. Notice that gamma becomes 1 when the velocity is 0, but it becomes infinity when the velocity it approaches the speed of light, because beta becomes 1 and gamma goes to infinity. Oh, and the opposite transformation, of course, is written like this. In this case, what is preserved is what is called the distance in this four-dimensional space now, made up of time and space, which is the difference in time and the difference in space. This is a constant which remains unaltered when you go from one frame to the other. So the sign of this quantity, which is the space-time separation of two events, let's call event a particular point given by a spatial coordinate x and xyz and time coordinate t, the separation in 4 dimensions with this strange metric, rather than having a square of a vector which is the sum of the square of the components. In this case, this is defined as the square of the time-like component minus the sum of the squares of the space-like components. This has to be preserved. The sign of this has to be preserved. I can move it around depending on the velocity in which I'm moving and the frame that I choose. But this separation is either positive, which means that the separation is mostly due to time. I can always find 2 frames or a frame such that 2 events occur at the same position but at different times. Or it can be negative, which means that the separation is space-like, which means that 2 events, I can find a frame in which 2 events occur at different positions but at the same time, so synchronously. This is not something that if you have never seen it before, I don't expect that you will digest it. The idea that time and space have to be mingled together in this transformation is particularly hard to understand. There are many introductory books of relativity. There is one that Einstein wrote, which is Relativity for Laymen. I forgot the exact title. I actually find it very confusing. There are much better texts that introduce this concept. But the problem is that it has been immediately verified experimentally. So the quantity that we want to deal with is this infinitesimal separation between 2 events. Einstein used a funny notation. He used the indices mu going from, depending on the metric that you use, whether we use it minuses for the spatial squares or minus for time. There is some notation in which you use an imaginary time, so this becomes a minus also. They're all equivalent. When you use the indices for this index, it goes over 4 numbers, either 0, 1, 2, 3, or 1, 2, 3, 4. If you repeat the index, you imply that you're summing over this index. So the x mu really means sum between 0 and 3, or 1 and 4, of dx mu summed over mu. Why up and down? I'm not going to spend too much time. Actually, this is not an arbitrary notation. You really need to sum only over up and down. And that's a question of the metric, which is not purely Euclidean. There is this minus sign floating around. Anyway, this quantity says what is the infinitesimal separation in space and time, in 4-dimensional space-time, between 2 events, which are infinitesimally closed. And we can express it this way. Clearly, if you can express the sum of the squares of the derivative, the differential in space, as the velocity times the differential in time, you can express it in terms of that function gamma, the component gamma that I wrote over here. So you see that it becomes just the separation between 2 events can be expressed just as infinitesimal of time with this velocity of light and the gamma. Now, one immediate verification, experimental verification of this fact, and I'll stop here for today and with this example, which is extremely convincing, I think, from the fact that it really time is a matter of perspective, not just position, is that if you look at the time as it flows in one frame with respect to the other, you see that the time distance, the difference in time between 2 events can change. So time dilates or contracts depending on how you're moving. In particular, it is interesting to express all time quantities using this expression, which is the proper time. So I'm moving with a particle, and the particle is at rest in my frame. this will be the proper time of that particle. Again, it's not the same speed at which time flows from an observer, which is seeing the particle moving at some speed. So the proper time is the time that is felt by the moving object. Now, the difference between two time intervals, T1 and T2, as seen by somebody, suppose that this is a particle which is coming from the upper atmosphere, a cosmic ray. And suppose that this is the clock, the time measured by the clock of somebody which is sitting at ground level, at the surface of the planet. So how does this relate to the time felt by the particle which is moving? Well, we see it here. I have essentially to convert this delta time, d tau over here, with this dt over here. And this implies the gamma divided by square, this object over here, okay? So the time that is seen by the clock that is observed by somebody sitting at ground level as a function of the time that is felt by the particle which is moving is very different. In particular, it goes much faster if the particle moves at the speed of close to the speed of light, because this number becomes extremely small. The experimental verification, the new mesons, they were called mesons at the time when this was observed. We know now that they're actually cousins or brothers of the electrons and the tau particle. They are leptons. But anyway, they were called mu mesons at the time. They're generated by high energy collisions in the atmosphere. They decay very quickly into electron and neutrinos, and they decay in about 2.2 microseconds. You go and calculate at the speed of light how much distance they cover. They cover less than a kilometer, about 660 meters. Okay, so we have a problem. Why do we see them at sea level? And the reason is because they go so fast. They go almost at the speed of light, so they can be detected some 10 to the 5 meters rather than 600 meters, simply because the time felt by the muon itself is stretched to a much longer time as seen by the observer, which is at rest on the surface of the Earth. So this is the famous time dilation. The opposite effect that one can see is the Lorentz contraction, in which an object of length L, as seen from an observer which is moving at some particular speed corresponding to this factor gamma, can be seen shorter than what is seen by somebody which is moving with the object itself. This was actually what was, it was an ansatz, wrong, well, wrong or right, depending on how you view it, which was proposed to explain the Michelson-Morley experiment. The fact that the speed of light was the same depending on whether the velocity of that light coming from a star was measured in January or June was supposed to be due to the fact that the interferometer that they used to measure the speed of light, actually a delay or a shift, was due to the contraction of the path that the light followed traveling towards or against the star or the motion of the Earth. And indeed, that is true, except that this was ad hoc assumption that Lorentz and Fitzgerald made, while Einstein proved it from his general consideration. So next time, I want to jump to the definition of the total energy of a particle, because this is what we will need to derive a relativistic wave equation, and then go finally to what we do to derive wave equation. And particularly here, I want to show the minimal coupling that we will also use. We've used already to look at acceleration theorem, but we will also use to calculate the interaction of radiation with matter. So for example, optical absorption. So I'll stop here. I'm really running out of voice, and we'll continue with this stuff next time. And then at the end, we will see the graphene, the tight binding model for graphene. And next week, we will start with what I think is the most fun and most interesting part of the class, which is quantum field theory, or second quantization, elementary excitations. That will be very interesting because it will require a change of mind, a change of outlook on how we view physics, in which the main objects will not be particles anymore, but will be fields. And we will have to start from there. So a change of perspective. So I'll be glad to answer questions if there are any. And otherwise,
yes, I have
yes.
a trivial question. I have not seen these slides in your site this morning. Will you allow us to download them?
Okay. There is, I think I posted somewhere a PDF called Appendix, which contains this. And I will post these slides today, maybe later on today or tomorrow. And I will also post the slides that I will use next week. Okay. But anyway, there should be a file called Appendix, which actually has a typo. I'll show you where the typo is. I fixed it. No, well, it's a typo that we haven't seen yet. When I go to trying and, where is it? The right Dirac equation. Talking about the quaternions. Okay. Come on, give me a pointer. This is a minus. It's in the slides, in the PDF that I posted, it's erroneous K plus.
Okay.
This is the fun story about Rowan Hamilton and the algebra, the quaternions. It's a story that I like very much as I like the story of Green, the guy behind Green's function. Maybe I'll tell you next time. If you don't know it, maybe you know it already. Okay, any other question?
Oh, Massimo, I have a short question. When you show the pseudo potential with graphene, I mean two-dimensional graphene, not nanoribbons, do you know how many plane waves they have to use for deriving the band structure of graphene? Do you have an idea of how many plane waves are necessary? I should have an idea
because these are my calculations, so I should know. Okay. Oh boy, I'm trying to remember. Yeah, I did it some 7 and 8 years ago. A few hundreds, but I don't remember exactly how many. For ribbons, we're talking about many more because it's a one-dimensional structure.
Yeah.
So I have to enlarge the structure both ways, right? Vertically and also on the width. I'll let you know for sure.
But in graphene, there are a few hundreds already.
There are already a few hundreds, yes.
Okay.
And that's because, well, it depends on what is the distance between the graphene sheets that you consider, right? You need some vacuum in the vertical directions, not to have the graphene sheets talk to each other. And I think I've used about 1.5 nanometers of vacuum, and that may be a few hundreds. But nowadays it's not very time consuming. So okay. Ribbons is a few more, yeah. Any other questions? Yeah. If not, have a good weekend. I appreciate very much your patience. What time is it for you now? It's 7 o'clock? Boy.
5 past.
Friday night. I spoil your weekends. I'm sorry about that.
No, not at all.
Okay, have a good weekend and
bye-bye.
Bye-bye. We'll talk next week.
Bye-bye.
Bye-bye.
Bye-bye.